Yeah, hello everyone. I hope the audio is clear now. Hello everyone. Yeah, good evening to all. Just let me know if it is audible or not. Yeah, good evening everyone. Yeah, my name is Ankit Dongriyal and I am your mentor from Civil Engineering Department. As you already know that IMS GATE Academy is running a GATE score booster session where our experienced faculties are dealing with some of the most important concepts and related questions for your upcoming GATE 2023. Right? This is just to boost your score so that you can plan your revision according to our series. You can plan your preparations according to our series. Right? So, in today's session, I am going to deal with open channel flow. Now, what will be the target audience? If you have already completed your open channel flow, this is going to be best revision video for you. But if you have not completed it yet, this particular video will give you the complete insight that what are the important parts in this open channel flow chapter, what are the important questions, and from which topic the question can be framed, what type of question can be framed, right? So, now as the word is open channel, can you tell me what is this particular open channel? Just for the example, if I ask you, can you tell me out of these two figures, this is your figure number 1, this is your figure number 2. Can you tell me which of the following is an open channel? Just can you tell me which of the following is an open channel? Yeah, thank you Nikhil. Can you tell me which of the following is an open channel? Okay, so we will discuss it later. By now, in this particular session, we will also deal that how we define a particular open channel. Okay, Nikhil Gaurav, it is both. Let's see if these both are open channel or 1 or 2 is open channel. Right? Before that, I'll just explain what will be the agenda for today's class. So, we are going to discuss that what is an open channel. Right? We will discuss about the different type of geometries and the geometrical properties related to an open channel. After that, we are going to discuss about the different type of flow which can occur in a channel. That's why the subject name is open channel flow. Clear? So we will discuss about this uniform flow. If the depth of flow, it is constant throughout the length, we call it as an uniform flow. But whenever there will be any transition either in the width or the depth of flow, there will be a non-uniform flow, and in that case there will be variation in energy and depth that we are going to discuss. Also we are going to discuss the gradually varied flow and rapidly varied flow. So this particular is the part which we are going to cover in this particular session, right? Now coming to our previous question, I have told you that I have asked you which of the following is an open channel. So yes, these both are your open channel. Pragya Tripathi has also answered the correct that these both are your open channel. Nikhil Gaurav also has a correct answer that these both are your open channel, right? Now let's see how we can define an open channel. As by the geometry we cannot say that these are the open channel, right? If we see its geometry is closed, its geometry is open. It means based on the geometry we have not defined any particular channel. Now what is the definition then? Now try to see this figure. This is the example of our first case. This is the example of our second case. These both are open channel. How we can say any particular channel? When we can say it as an open channel flow, if any liquid is flowing through a channel with a free surface, that particular channel we call it as a open channel. So the key word here is your free surface. If any channel it is having a free surface, you will say it is an open channel. Now the next question arises in our mind, sir, what is this free surface? Now beta, free surface is that particular top surface at which your pressure is constant. What is the definition of a free surface? Any surface which is having a constant pressure, that will be your free surface. Now if we see this particular surface of liquid, This is having a pressure. Generally, it will be atmospheric pressure in our case, and the liquid will be water, right? So mainly we are going to deal with water, and in these cases, the pressure will be what? Atmospheric pressure. And we know this is a constant pressure, right? So here also there is a constant pressure. So this is a free surface. In this particular case also, we can see that this is a free surface having a constant pressure. So this will also be considered as a free surface. I hope this particular doubt is clear now, right? Now, if we see these particular channels, open channels, they can be either man-made or artificial. Now, let's see this particular image. In this particular image, you can see a natural stream, right? So this particular natural stream is also an example of open channel. How we can say it as the open channel? As this particular channel is having a free surface. Here you can see the schematic diagram of this particular channel. This particular surface, it is having a constant pressure. It is having a constant pressure. That is your atmospheric pressure. So this is also your open channel. Your open channel can also be the artificial channels, right? And in artificial channels, it can either be having an open cross section like this. In this particular case, you can see, or it can have a closed cross section also. It can also have a closed cross section or covered cross section also. Now, out of these two, we are going to discuss about the artificial channels, or you can say man-made channels. Clear? Now, in the category of man-made channels also, we are going to discuss about one particular type of channel, that is our prismatic channel. That is our prismatic channel. So, we are mainly dealing with our prismatic channels in this particular syllabus. Clear? Now, again the question will arise that what is this prismatic channel, sir? Now, this prismatic channel, it is that channel which is having a constant cross section and a constant bottom slope. If your cross section is constant and if your bottom slope is constant, then you can say that particular channel to be prismatic. Now, what is this constant slope? If let's suppose this is the side view of any channel, this is the side view of any channel, this is the depth of flow, right? Now the water is flowing like this. Let's suppose water is flowing like this. Clear? This is the channel bottom. Now the angle made by channel bottom with respect to horizontal, that is nothing but your bottom slope, right? Or if it is that constant bottom slope, you will call it as a prismatic channel. Also, there is one more condition, that there should be a constant cross section. There is one more condition, that it should have a constant cross section. Now, what is the meaning of cross section? If we take a section perpendicular to this base of the channel, again remember, if we take the perpendicular to this base of the channel, that will be our cross section. That will be our cross section. There can be a vertical line also. There can be a vertical line also. Remember, there can be a vertical line also, but we have to see the perpendicular line, right? So perpendicular to this, the section will be our cross section, right? Now this is having a depth y, this is having a depth d. Generally, we call this depth as depth of flow section. This is its depth of flow section. And this d, we call it as the depth of flow. We call it as a depth of flow at any particular point. But generally, the slope of the channel used to be very less. If the slope of channel is very less, you can consider that this y and d are same, right? These y and d will be different if the channel slope is very high. But as generally the slope of the channel used to be very small, so we consider these to be as the same, right? But if in any particular question, it is given that there is a depth of flow of section and there is a depth of flow, so the cross section dimension is our depth of flow section. I hope it is clear to you, right? Now, it means if we are dealing with this cross section, it means how much discharge can flow through the channel. How much discharge can flow through the channel? that will depend upon the characteristics. That will depend upon the characteristics of this particular cross section. So there are different parameters, or you can say the geometrical parameters related to this cross section. There are the different geometrical parameters related to this cross section which will help you to analyze the type of flow, right? Our main agenda is to analyze the type of flow, what will be the discharge through any particular channel. Clear? So we need to study what are the different geometrical properties related to any particular open channel. Clear? Now, if we move to that particular part, these are the different geometrical parameters related to any particular channel. Now, what are these geometrical elements? See, one is your top width. Generally, we denote it with T. What is this top width? The width at the free surface of water. The width at the free surface of water. This width at the free surface of water. This width is your top width, right? Second is your wetted area, or sometimes we call it as a water area. What is this wetted area or water area? This wetted area is nothing but the area covered by this water. The area covered by the water in this particular cross section, that is nothing but wetted area or water area. Clear this thing? Right. Now, third is your wetted parameter denoted by P. Now, what is the wetted parameter? Wetted parameter is that particular length which is in contact with the water. It is the length of the cross section of the channel which is in contact with water, right? What is a free surface? Okay, so we have discussed that what is a free surface? Any particular surface which is having a constant pressure, that is our free surface. I hope it is clear, right? Now try to see. Here try to see wetted parameter. What we have discussed, what is a wetted parameter? Wetted parameter is the length which is in contact with the water. The length of this particular cross section which is in contact with the water, that is your wetted parameter. Clear? So it is the length of the line of intersection of channel and wetted surface area. Clear this thing? Now, next parameter is our hydraulic radius. This hydraulic radius, it is the ratio of your area and wetted parameter. It is the ratio of your area and wetted parameter. Sir, why we are reading these things? As these particular cross-sectional parameters, they are going to use in the calculation of discharge through any particular channel, right? And on the basis of this particular discharge, we are going to construct all our channels. Clear this thing? So these channel geometries, depending upon the discharge, you have to decide these channel geometries, and then that particular channel, it will be beneficial for that particular discharge. I hope it is clear. Next geometrical parameter is your hydraulic depth. It is nothing but the ratio of your wetted area to top width. Clear? So these are the some of the geometrical parameters. One is top width, one is your wetted area, one is your wetted parameter, next is your hydraulic radius, and next is your hydraulic depth. Clear? Now let's see how we calculate these parameters. Clear? We will focus now how to calculate these parameters. Okay, I have taken the most generalized case, the case of this particular trapezoidal section. Clear? I am just going fast so that in this particular 3 hours we will be able to cover this particular open channel flow. Clear? Now try to see, this is the particular generalized case, this is your trapezoidal channel. So we will try to find out the different geometrical parameter for this trapezoidal channel. For this trapezoidal channel. For this trapezoidal channel. Now can you tell me, for this particular trapezoidal channel which is having a base width as B, having a depth of flow section as Y, and having the side slope as 1 vertical to m horizontal. Now this is particularly the representation of your side slope, right? What does it mean? It means that it is 1 vertical to m horizontal. Sometimes like this also you can find out. Clear? What is the meaning of this 1 vertical to m horizontal? It means when you are moving 1 unit in vertical direction, you have to move m unit in horizontal direction to make this particular slope. Clear? Now try to see. If we find out the different geometrical properties for this trapezoidal channel, we'll start with the top width. That is nothing but t value. Now you know that the top width is nothing but the width at the free surface. It means we need to find out this particular value. This is your top width. Clear? How to calculate this particular value? Now try to see. I know that this particular distance is nothing but b. If the bottom width is b, this value is also going to be b. Right? Now if I am moving y distance in vertical direction, I have to move m into y or m times of this particular distance in horizontal direction to keep this slope. It means this particular value, it is going to be m into y. Right? And this value will also be m into y. So what will be my top width? Can I say top width is b plus my plus my? So it is nothing but your b plus 2 times of my. Clear? Next thing. Next cross-sectional characteristic, that is your wetted area. Denoted by capital A. Now wetted area is this particular area of water. The area which is covered by the water in this cross section, that is nothing but your wetted area. How to calculate this wetted area? This particular part is nothing but a trapezoid. We know the area of trapezoid, it is half sum of parallel sides into length. A very good evening to everyone. Right? Now let's try to find out the area of this trapezoid. It is half sum of parallel sides into this particular distance between these parallel sides. What will be this value? This bottom width, can I say this area? It is going to be equal to half. This base width is b plus top width. Top width is our b plus. I'll just keep it as small b only. Right? As we have used this as small b. Clear? Now it will be b plus top width, b plus 2my into the distance between these parallel lines, that is y. So it is going to be equal to b plus my into y value. Clear? This is nothing but your wetted area. Now next property is your wetted parameter. Next property is your wetted parameter. Right? This is your wetted perimeter. What will be this particular value? It is denoted by P. This wetted parameter, it is the length which is in contact with the water. It means this particular length plus this length plus this length. Now this we know it is a b value. What will be this particular distance? What will be this particular slope? If I take this particular triangle, I know this distance is y. I know this distance is my. So by the Pythagoras, can I calculate it as this particular distance? It is nothing but under root of y square plus m into y square. Or I can say it is at y under root of 1 plus m square. This is the length of one side slope. Clear? So what will be the particular parameter value? It will be this one slope plus second slope plus this bottom width. So it will be what? It is going to be equal to b plus 2 times of your the slope value 1 plus m square. Clear? Now I hope it is clear to you. Now if wetted area is known to me, top width is known to me, wetted parameter is known to me, the ratio of your wetted area upon wetted parameter, that will be your hydraulic radius, and the ratio of your wetted area to top width, it is going to be your hydraulic depth. I hope it is clear. Now I hope you will be able to calculate these particular geometrical parameters value for any type of cross section, right? Either it is a rectangular cross section, either it is a triangular cross section. Clear? Now let's move to next part. By now we have talked about only the channel. Now we are going to discuss about the type of flow in that particular channel, right? Now in open channel, based on the criteria of time, we can define the flow as steady flow and unsteady flow. Now what is this particular steady flow? If the flow properties, they are constant with respect to time, if the flow properties are not changing with time, right? Let's suppose in any particular channel you have seen the depth of flow, it is, let's suppose, 1 meter at particular time. After 1 hour still it is 1 meter, after 1 hour still it is 1 meter, right? It means we can say with time the depth of flow, it is not changing, or the depth of flow is nothing but your flow property. There can be different flow properties like velocity, like discharge, right? But here we are more concerned about the depth of flow. So if depth of flow, it is constant with respect to time, we will call it as a steady flow. But if the flow properties are changing with respect to time, we will call it as a unsteady flow, right? So this dy by dt, it is nothing but change in the depth with respect to time. It is, if it is not equal to 0, it means it is changing. Clear? Now based on the space, or you can say the length, also we can define the different types of flow. So based on the space also we can define the different type of flow. If with respect to space your flow properties are going to remain constant, it will be considered it as a uniform flow, right? So if your flow properties now they are not changing along the length of the channel, they are not changing with respect to length of the channel, so you can say it is a uniform flow. But again, if these properties are changing, it will be your non-uniform flow, or we can say a varied flow. Non-uniform flow, or you can say varied flow. Clear? Now this varied flow, it can be gradually varied. What will be the meaning of gradually varied? Let's suppose I am saying that with respect to length, if the flow properties are changing, right? We are talking about the depth of flow. Now if depth of flow, if your depth of flow, it is changing gradually, you will say it as a gradually varied flow. But let's suppose the depth of flow, it is changing suddenly, we can say this particular type of flow, it will be a rapidly varied flow, right? So in this particular category there will be a gradually varied flow. So we are going to deal with this uniform flow, we are going to deal with this gradually varied flow, or we are going to deal with this rapidly varied flow, which are related to steady flow, right? So we will deal with uniform flow, we will deal with gradually varied steady flow and rapidly varied steady flow. Clear this thing? So these are the points which we need to cover. In unsteady flow also there can be varied flow, although if the flow is unsteady, in nature we generally will not find out that the flow is uniform also. So it will be generally a gradually varied flow, which can be gradually varied or rapidly varied. I hope it is clear. So by now what we have discussed about the channel, we have discussed about the type of flow in that particular channel, right? So we have discussed that what is an open channel, a channel which is having a free surface, that will be your open channel, right? We have seen the different geometrical properties related to cross section, and now we have discussed about the what are the type of flows which are possible in this particular channel. Now these two combined things, it will make a open channel flow. Clear? Now first we will deal with this open channel flow, this particular uniform flow. Here in this diagram also you can see, right? If the depth of flow, it is changing gradually. In this particular portion you can see the depth of flow, it is changing gradually. In this particular, you can say that here the depth of flow is very high, right? And after that it is suddenly changing. So in this particular portion, if you will see, this is a rapid change in the depth of flow, yes or no? So this particularly it will be your rapidly varied flow. This will be your rapidly varied flow. Now in this particular case, if you see, in this particular portion, the depth of flow is changing, but this change in the depth of flow, it is very minimum. So that's why you are calling it as a gradually varied flow. But if the flow depth, it is constant with respect to space, let's suppose in this particular portion, so it will be considered as a uniform flow. Clear? Now as you know that in an open channel, the force which is responsible for the flow, it is nothing but your gravity force, right? Like you have seen in a pipe flow, the viscous force are predominant, but here the predominant force is your gravity force. So one dimensionless number defines this particular gravity force, that is your Froude's number, right? So based on Froude's number also we define the different types of flow. Now let's see what are the different type of flow depending upon the Froude's number, and what is this Froude number. Clear? So this Froude's number, it is nothing but it is the ratio of your inertia force and gravity force. So inertia force and gravity force ratio, it will give you Froude's number. Defined by Froude's number is V upon under root of GD, right? Now this D, it is nothing but your hydraulic depth, which we have defined as a characteristic. So this is your hydraulic depth. Clear? Hydraulic depth, nothing but area upon top width. Clear? Now in open channel flow, depending upon this Froude's number, we can have three types of flow. One is your supercritical flow. If the Froude number is greater than 1, you will call that particular flow as a supercritical flow, right? If the Froude's number is equal to 1, that flow will be your critical flow. But if the Froude number is less than 1, it will be your subcritical flow. It will be your subcritical flow. It will be your subcritical flow. Clear? I hope it is clear. So depending upon the Froude's number, it will be your supercritical flow, critical flow and subcritical flow. Now if you see this particular value, this particular V, it represents the velocity of flow. It represents the velocity of flow, right? Whereas this particular under root of GD value, it mainly represents the velocity of a wave. Velocity of a wave. This particular value represents the velocity of wave. So sometimes the question can arise based on the practical properties, how you can define any particular channel it is having, if it is having a critical flow, subcritical flow or supercritical flow. Now let's see. Yeah, good evening. Good evening, Sanjay. Now, depending upon your Froude's number also, we can see that there is a subcritical flow, supercritical flow and critical flow. But on the basis of practical observations also we can define. Let's suppose in any particular channel, if this is the direction of flow, this is particularly the direction of your flow, right? Now, if V is less than under root of GD, this V value is nothing but velocity of flow. This under root of GD, it is nothing but your velocity of wave. So if let's suppose you have created the waves, let's suppose you have thrown any particular stone in a particular stream, it will create the waves around that particular point. Now depending upon the pattern of that wave, you can tell that if that in that channel the flow is critical, subcritical or supercritical, right? So if the velocity of flow is more and if it is a subcritical, it means your velocity of flow, it is going to be less. and the velocity of wave, it will be more. So you will find out that if this is the particular point of where you have created this particular obstruction, so you will see that the waves, they are moving both in upstream and downstream direction. But if you see the critical case in this, the velocity of flow and the velocity of wave are same, right? It means this velocity of wave or these waves, it will not move in the upstream direction. You will find out a pattern only in the downward direction. Clear? And it will be starting from this particular point. Clear? Now if it is a supercritical flow, this V is going to be greater than GD, right? So the V is the velocity of flow and this under root of GD, this is the velocity of waves. Now this water, it will force the wave to move only in the downward direction as they are having a greater velocity. It means now the waves, they are only going to move in downward direction. Clear? So these are the practical observations on the basis of which you can define any particular flow, if it is subcritical, supercritical or critical, right? So once in the GATE exam also they have asked such type of question. Clear? Okay, in this particular chapter we are also going to see some of the most important equations which will help you throughout this particular series, right? So one is our continuity equation. So continuity equation is mainly there is no change in the discharge value. Clear? So discharge at any particular section, it will be same at any particular other section, right? So it means at any particular section, if I take this is our section number 1 and this is your section number 2, this is your section number 2, this is your section number 1. So whatever is the discharge at this particular section 1, same discharge you will get at section number 2. It means the storage we are not taking into account. Clear? Second thing is your energy equation. Second thing is your energy equation between two lines, right? So the energy between two lines, the total energy, it is going to remain same if you will neglect the losses, right? But if there is a loss at any particular section, there can be three type of energies. One will be due to this particular head from the datum, we call it as a datum head. So this particular distance, we call it as a datum head. This depth of water, it will give you the pressure head value and there will be some velocity in this water. Due to that also there will be one energy. Now the head corresponding to that velocity, we call it as a kinetic head or sometimes we call it as a dynamic head. Clear? That will be given as V square upon 2G. Clear? So these are the energies at any particular section. So this energy, it is going to remain constant. Clear? If there will be no head loss. Now this head loss in any particular channel, if water is flowing, the head loss can be due to two reasons. If we talk about the open channel, these head loss can be due to two reasons. One is head loss due to friction and second, the head loss due to eddies. Clear? Sometime you might have seen in an open channel, the water is flowing like this in the ripples, right? So these ripples are nothing but these are the eddies. So due to the formation of these eddies, there will be an eddy loss and now this eddy loss we cannot calculate. It means this particular energy equation we generally use in only to analyze those type of flow in which eddy loss will be very less, where we can neglect this particular value. Clear? If in any particular type of flow, these eddy losses are very high, we are not able to use this particular equation. In that particular case, we will use our momentum equation. So this momentum equation says at any particular fluid element, the algebraic sum of forces, it will be equal to the rate of change of momentum. I have written here the final result. This is particularly your A into Z plus Q square upon AG. This is your specific force. This specific force will remain constant. Like this also you can say, right? As this is the particular relation we are going to use in this particular chapter. So, right? So this A into Z plus Q square upon AG, it will be your constant. This particular term, it is nothing but your specific force. That also we are going to see later. Clear? What is this A? This is the area of cross section of, or you can say the wetted area. What will be this Z value? This Z value, let's suppose this is a triangular channel. So this Z value, it is the distance of CG of this particular area. It is the distance of the water area from the top surface. So this value is your Z bar. This particular value is your Z bar. Q, it is nothing but a discharge value, and A, again it is a your area, or you can say wetted area. I hope it is clear, right? So this specific force, it is going to remain constant. So whenever there will be eddy losses, and if we cannot neglect those losses, we will use this particular momentum equation. Clear? Otherwise, in other cases, we can also use this energy equation. I hope it is clear. Now we will talk about the uniform flow. First type of flow that we are going to discuss in this particular channel is uniform flow. Now we have already discussed that uniform flow means if the flow property, which flow property? The depth of flow. If it is not changing with respect to space, then we will say it is to be a uniform flow. Let's see here. If I'll take as a section number 1, and if I take this as a section number 2, the depth of flow, it is Y here, and depth of flow is Y here, right? We know in between these two sections, the discharge will also be constant. Also, we are dealing with the prismatic channels. It means the channel prismatry also cannot change. It means, can I say the velocity at this section, if it is V1, and if it at section number 2, this velocity is V2, this velocity values are also going to remain constant. These velocity values are also going to remain constant, right? Now let's suppose if I represent the slope of this channel bottom, with S0, right? This line which is at the top of this particular free surface, this particular line we call it as a hydraulic gradient line. And the line which is representing the total energy at particular section, it will be nothing but your total energy line, or you can just say energy line. Clear? So this particular, if I say this particular top surface, I can say this is a water surface. Let's suppose it is having a slope SW. And this energy line, it is having a slope with respect to horizontal, let's suppose SF. So we have defined 3 types of slope. Your SF value is the energy line slope, your SW is water surface slope, and S0 is your channel bottom slope. As the depth of flow, it is not going to change, right? Your velocity, it is not going to change. It means this energy value also not going to change at any particular section. Clear? Also, we have considered the prismatic channel. It means the slope is also not going to change. So can I say for a uniform flow, all these 3 values are going to remain same? So your water surface slope and your energy line slope and your bottom slope, they are going to remain constant, right? So generally we use this slope value for the calculation of discharge, right? As our main agenda is to find out the discharge in any particular channel. Clear? So even if it is given you the S0, you can use SW and SF also. Clear this thing? Now the main point here is how we can calculate this discharge. Now for the calculation of discharge in the uniform flow, we have 2 equations, right? One is given by Manning's and another is given by your Chazy's equation. Clear? So this is your Chazy's equation and this is your Manning's equation. Generally these values, it will give you the value of velocity, right? What is this Chazy's equation? It is given as V is equal to C under root of R into SF. Now I have told you that this hydraulic radius, it is going to be used for the calculation of discharge, right? You remember this R value, this is nothing but hydraulic radius, that is area upon wetted parameter, We have seen it is on cross-sectional properties, right? This SF, it is your energy line slope. This is your energy line slope. Remember, in the original formula, it is the energy line slope, right? And this C value is nothing but your Chase's coefficient. Now this Chase's coefficient, it is generally a roughness coefficient. As we know, when the water is flowing through the particular channel, that particular channel geometry or channel material, it will have some roughness. So depending upon that material value, this Chase's constant will be there, right? Also you can calculate it with the help of C is equal to under root of 8g upon F, right? What is this F value? This F value is nothing but your friction factor. Friction factor. Clear this thing? So note, for a uniform flow, we have seen that for a uniform flow, S0 is equal to SF. So in case of this particular SF value, you can also use this S0. As generally when you'll see the questions, right, maximum time the examiner will give you the channel bottom slope, right? So remember, if the flow is uniform, you can use S0 value in case of SF, right? For a uniform flow, what will be the case? For a uniform flow, this velocity will be now C into under root of R into S0. This will be true only for your uniform flow. This will be true only for your uniform flow. Now according to Manning's, this velocity is given as 1 upon n r to the power 2 by 3 sf to the power 1 by 2. Clear? What is this n value? N value is again the Manning's roughness coefficient, right? Depending upon the different material of this channel, they have given this n value. This will be given to you by the examiner. Next thing is your hydraulic radius. Hydraulic radius is nothing but your area upon wetted parameter. Again you have to calculate depending upon the geometry of your channel, and SF is your energy line slope, right? In case of SF, if the flow is uniform, again you can use S0 value. You can use the channel bottom slope also. Now we know that discharge will be nothing but area into velocity. We know discharge is equal to area into velocity. So by Manning's equation, the discharge value is given as Q is equal to 1 upon n A r to the power 2 by 3 SF to the power 1 by 2. Similarly, if we write from the Chase's equation, it will be what? Q is equal to C into A into under root of R into SF. Clear? So this is according to Manning's, this is according to Chase's. So generally a question will ask from this particular chapter any of these value, it will keep it as an unknown, other values will be given to you and you have to calculate that value, right? So this is the first type of question which is generally asked from this particular chapter. Second particular important point from this chapter is your efficient channel, right? Now what should be the geometry of any particular channel? What should be the characteristics of any particular channel so that it can carry a maximum discharge? That will be your efficient channel. Also we call it as an economical channel. If your channel can be made cost effective, it will be your economical channel. Now what are the characteristics related to that? Next thing we are going to discuss about the most efficient channels. Now let's suppose this is particularly your rectangular channel, right? When we can say any particular channel to be most efficient, first thing is when your discharge is maximum. If the discharge in any particular channel, it is maximum, can we say that is the most efficient channel? For most economical, what should be? Its cost should be effective, right? Now mainly if in a channel we see, mainly the cost is of this cost of lining, right? It means a channel which will have the minimum wetted parameter, a channel which have a minimum wetted parameter, it is going to be your cost effective, right? So your wetted parameter P, it should be minimum. It should be minimum. Now let's see if the parameter is minimum. See, if the parameter is minimum, can I say that the resistance which is provided against the flow, it will also be minimum? As the friction to this particular water flow, it is due to this particular parameter. Now if this parameter is minimum, I can say the losses will be minimum. If losses will be minimum, my discharge is going to be maximum, right? So the important property which defines any particular efficient and economical channel, that is your parameter should be minimum. Clear? Now we'll try to find out that what are the different properties related to the most economical triangular channel, trapezoidal channel and your rectangular channel, right? So let's suppose this is your rectangular channel having a width b and depth of flow as y. So I'm not going to discuss it in detail, but I'll just give you the values that when you can say a rectangular channel to be most economical, right? So if the width of channel, it is 2 times of y, or you can say when the water, it is flowing at half the distance of this particular width, you can say this particular channel, it will carry the maximum discharge, right? And it will have a minimum wetted parameter. Clear? So if b is equal to 2y, we can find out the different properties like top width. What will be your top width? Top width will be equal to nothing but b only, so it will be equal to 2y. Next geometric property which we can define, that is wetted area. So area of this particular channel will be b into y. Your b value is equal to 2y, so I can say it is 2y square. Third thing is your wetted parameter, right? So wetted parameter, we know this particular length, this length is y, this length is 2y, this length is y. Clear? So can I say wetted parameter is y plus 2y plus y? It is 4 times of y. What will be hydraulic radius value? That is area upon wetted parameter. So it is 2y square upon y upon 4y, that is equal to half of y value. Half of y value, right? And last property if we see, that is hydraulic depth, that is area upon top width. So what will be the area upon top width in this case? Area is 2y square and top width is 2y square and top width is your 2 times of y. Clear? So it is equal to y value. It is going to be equal to y value, right? So these are the geometric parameters for your most efficient and most economical channel. I hope it is clear. Similarly, we can find out for different cases. Let's see for a triangular channel. Now the condition for a triangular channel to be most economical, that either you can remember like this, it should be a square. It should be a square having a side of root 2y with a diagonal horizontal. Remember, if the diagonal of this particular channel, it is horizontal, and if you make it as a square, this will be nothing but your, this part, it will be your most economical trapezoidal channel. Sorry, most economical triangular channel, right? Now, if I say this is a square, it means this particular angle will be 90 degree. This particular angle will be 90 degree and this theta value will be 45 degree. This angle will be equal to 45 degree, right? What will be the one vertical to m horizontal? If this particular value is 45, if this particular angle is 45, can I say this value and this value will be equal? So m value will be equal to 1. So what are the different properties? So first I'll write properties. First is your, this we call it as a apex angle. This particular angle we call it as a apex angle. So in apex angle, it should be equal to 90 degree. So first condition is apex angle is 90 degree, or you can say this side slope, it should be, side slope will be what? Your side slope will be 1 vertical to 1 horizontal. Clear? Now remember this particular figure, this particular dimension will be root 2y. this will be root 2y. If this particular value is your y, this is also y, this is value is also y, right? Now based on this particular characteristic, again we can find out the different hydraulic properties, or you can say cross-sectional geometrical properties. First is your top width. What will be the top width? Can you answer? What will be the top width? Can you answer what will be the top width? Anyone? What will be your top width for this particular channel? I have told you the characteristics of this most economical channel. Yes, it is going to be equal to 2 times of y. It is going to be equal to 2 times of y. Right? So this is your top width. Can you tell me what will be the wetted area? What will be the wetted area? It is going to be the area of this particular triangle. Right? It will be half base. What is the base width? 2 times of y. And what is the height? It is y. So it is nothing but your y square value. Yes, Prashant. Right? It is going to be equal to your y square value. Clear? Next hydraulic property, that is wetted parameter. So wetted parameter, directly we can say it is root 2y. This particular dimension, this is root 2y, right? So it is going to be root 2y plus root 2y, that is 2 root 2y. That is 2 root 2y. I hope it is clear. Right? Similarly, we can find out hydraulic radius value, that is area upon wetted parameter. What is your area? Area is your y square. What is wetted parameter? 2 root 2y. So it will be what? Y by 2 root 2. It will be your y by 2 root 2. And what will be hydraulic depth? Area upon top width. It will be area upon top width, right? What is the area? Area, you can say y square. Area, you can say y square upon what is the top width? It is 2 times of y. So it is going to be y by 2. It is going to be equal to y by 2. I hope it is clear. So again, these parameters, we have seen that they are used for the calculation of discharge, right? So if it is given that you need to find out the maximum discharge condition, right? Or if it is asked that there is a minimum wetted parameter, or if it is asked, or if it is mentioned in the question that it is the most economical or most efficient channel, so these properties directly you can take, right? In that particular case, examiner will not give you this particular slope value, as you should know that if any particular channel, if it is carrying a maximum discharge, it will have a slope of 1 vertical to 1 horizontal. This particular characteristic you have to remember. Clear? Now, if we see for a trapezoidal channel, if you draw a regular hexagon, this half of this regular hexagon, it is nothing but your most economical or most efficient trapezoidal channel, right? Now we know that in regular hexagon, these dimension will be same. And what is the dimension of that regular hexagon? It is 2 by root 3 of y. So this dimension will be 2 by root 3y. This dimension is 2 by root 3y. All the points, this is also 2 by root 3y. This is also 2 by root 3y, right? Clear this thing? Now, but we are more concerned about this particular part. This trapezoid part, it is our most efficient and most economical trapezoidal channel. Clear? Now, if these properties are known to me, this particular is y. Here, the theta value, we generally take it as this value. This theta value. If let's suppose it is having a slope of 1 vertical to m horizontal, 1 vertical to m horizontal for most economical channel, if I say this particular, it is a part of your regular hexagon, so this theta value, it is going to be equal to what? It is going to be equal to 60 degree, right? And what will be this m value in this particular case? It will be 1 by root 3. Clear? So what are the characteristics? Let's say the characteristics are, there are two types of cases. One in which if the side slope it is constant, if side slope is not a variable, if the side slope of this particular channel you cannot vary, right? Now in that particular case, what will be the dimension of this particular trapezoidal channel which can carry the maximum discharge that we are going to see, or that particular channel which will have the minimum weighted parameter that we are going to see, right? So if the side slope is already given to you, you cannot change this side slope. For that case, the condition will be half of the top width, it will be equal to the length of side slope. It will be equal to the length of your side slope, right? It will be equal to the length of your side slope, will be equal to length of side slope. Clear? If let's suppose this is having a 1 vertical to m horizontal, we know what will be this particular dimension. It is going to be y under root of 1 plus m square. This particular side, it is going to be y under root of 1 plus m square. So I can say that this t by 2, it is nothing but equal to y under root of 1 plus m square. This is the first condition. Second condition is, your second condition is r value, that is hydraulic radius value, that is going to be equal to y by 2. That is going to be equal to y by 2. So if the slope of channel you cannot vary, so these two properties are for the most economical trapezoidal channel. But if you can vary the slope also, what will be the value of slope? Second case is if slope is variable. If slope is variable. So for what value of slope you will get the maximum or most efficient channel, that this m value is going to be equal to 1 by root 3, or you can say it is 1 vertical to 1 by root 3 horizontal. Clear? Or also you can say this particular angle, the outer angle is theta, will be equal to 60 degree. So if any of the property it is given to you, you can take this trapezoidal channel having a regular hexagon, half of the regular hexagon having the dimension is equal to 2y by root 3. I hope it is clear, right? Now we have seen the calculation of discharge, we have seen the properties related to the most economical and most efficient channel. Now we can see what are the type of questions that can be asked, right? That is the mainly point of discussion here. So now try to read the question. This is your MCQ type question, right? The theory related to this we have already covered. Just read the question and try to find out the answer. Just once read the question and try to find out the answer. Try to see what is asked in this particular question and what you need to find out. Just read the question and try to find out the value. It is given that a rectangular channel of width 4 meter. So width of channel is given to you, having a bed slope of 1 in 1500. Bed slope is given to you. Find the maximum discharge through the channel, and you need to find out the maximum discharge through the channel. And you need to find out the maximum discharge through the channel, right? Changes constant is given to you. It means you need to find out this discharge value by using the Changes equation. Clear? Can you find out? Can you find out? I'll just draw the figure for you. Let's suppose this is your rectangular channel, right? Width of the channel is given to you that it is a 4 meter. That it is 4 meter, and Changes coefficient is given to you. and Chase's coefficient is given to you, that is C value. It is equal to 50. It is equal to 50, right? So how to proceed with this type of question? Let's try to see. First, we need to find out the discharge, right? So we know that we are having two formula for calculation of discharge. One is based on the Manning's equation, second is based on the Chase's equation. If Chase's constant is given, it means it is definite that we need to find out the discharge value depending upon this Chase's equation. So if I write the Chase's equation for calculation of discharge, we know that Q is equal to C under root of R into, now we are dealing with here uniform flow, so I can use S naught value into area. Clear? Now the important point is here maximum discharge. As you know, for the calculation of R, you will need this depth. For calculation of area, you will need this depth, but this depth is not given to you. So it should be known to you that if this channel has to carry the maximum discharge, it means it should be most efficient channel. In that case, this Y value should be equal to, half of its width, that is 4/2. That is nothing but 2 meter. This depth should be equal to 2 meter. Now can you calculate the discharge value? C value is given to me, that is 50. A value can I calculate? A value, it will be B into Y. What is the B value? That is 4. What is the Y value? That is 2. That is 8 meter square, right? Now we can also calculate R value, that is area upon wetted parameter. Let's calculate the wetted parameter first. Your wetted parameter, it will be this distance 2, this distance 4, this is distance again 2. It means 2 plus 4 plus 2, that is equal to what? 8 meter, right? So what will be the R value in this case? R value is going to be your R value, that is area upon wetted parameter. Area is your 8 meter square, wetted parameter is also 8 meter. It means this value will be 1 meter. Now I can calculate the discharge. Q is equal to C. C value is given to you as 50 into under root of R. R value is nothing but 1, right? Into SF, or in case of SF, I can use this S naught value, the channel bottom slope, that is 1 in 1500. That is 1 in 1500. 1 in 1500 into area. Into area, that is, we have already calculated the area, that is 8 meter square. Just solve this particular value and give me the value of discharge. Solve this value and give me the value of discharge. Give me the value of discharge. It is 10.32. It is equal to 10.32 meter cube per second, right? So this is the maximum discharge which can flow through this particular channel. Clear this thing? Now try this next question. Try this next question. Very good, Prashant. Now read this question and try to see what you need to calculate. A slightly roughed brick line, it means the channel material is given to you and it is nothing but, it is given as your Manning's roughness coefficient, right? For this particular material, what will be the roughness coefficient? It is given to you that 0.017 trapezoidal channel carrying a discharge of 25 meter cube per second. This channel is carrying a discharge of 25 meter cube per second to have a longitudinal slope. This is the channel bottom slope, 0.0004. the depth of flow for an efficient trapezoidal section having a side slope of 3 horizontal to 2 vertical is. Side slope of trapezoidal channel is also given to you, and it is asking for the depth of flow. That means y value. That is y value. And for which case? For efficient trapezoidal channel. For efficient trapezoidal channel. Can you calculate? Can you calculate? Just for your reference, I'll draw this particular case. Let's suppose this is the particular channel having a depth of flow that is equal to y, right? Channel base, it is not given, n value is given to you, and side slope is given to you. It is 3 horizontal to 2 vertical, right? And longitudinal slope is given to you, that is S0 value, which is nothing but 0.0004, and also given to you the value of discharge, that is Q, it is nothing but equal to 25 meter cube per second, right? This is the data given to you. Also, it is mentioned that this is the efficient trapezoidal channel. Also mentioned that it is the efficient trapezoidal channel. Now try to find out. Try to find out this depth value. Try to find out this depth value. Now, what will be the difficulty in calculation of this depth? We know that we need to find out. We can use the Manning's equation for this discharge. Now, when you will use this discharge value, Q is equal to 1 upon N. Q is equal to 1 upon N. A R to the power 2 by 3 into S0 to the power 1 by 2. Now, this Q value is given to you. This N value is given to you. We know that this A and R, it is going to be the function of Y, and it is also going to be the function of this base width B. This base width B, right? And both these values are unknown for me. This S0 value is also known to me. This S0 value is also known to me, right? It means I have to convert this particular equation such that there will be only unknown, that is the depth of flow. It means I have to eliminate this B value. Now, to eliminate this particular B value, it is given that this is a efficient trapezoidal channel. This is a efficient trapezoidal channel. And now remember, we have seen two type of cases in a trapezoidal channel. What were those two cases? In which we can change the side slope, and second is in which we cannot change the side slope. If you see this particular value here, side slope is given to you. It means side slope you cannot vary, right? Here the side slope cannot vary. It means you have to apply the condition number 1. Clear? So from condition number 1, apply that condition and try to find out a relation between y and b, and replace this, but in this particular equation, this b parameter in terms of y. That will give you the y value, right? Try this particular question. Try to find out. Try to find out. Let's try this particular question. I hope it is clear. Just let me know in the comment box if the process is clear or not. If you are trying, just let me know in the comment box so that I'll give you some more time, or otherwise we can discuss the solution. Just let me know in the comment box if it is clear or not, if you are trying or not. Otherwise, we'll go with the solution. I hope the question is clear. What it is asking, it is also clear. Yeah. Okay, it is clear, right? So should I move with the solution part? In meanwhile, you can also try, right? And if you got the answer, you can also let me know. You can also let me know. Clear? So we know if the side slope is given for most efficient trapezoidal channel, for most efficient trapezoidal channel, we know that half of the top width, it is going to be equal to length of side slope, that is y under root of 1 plus m square. Clear? Just for your reference, I'll again draw that trapezoidal channel. So this is your trapezoidal channel. This is your depth of flow section, that is y value. Let's suppose this width is b. Now side slope is given to you. Side slope is given to you that 3 horizontal to 2 vertical. 3 horizontal to 2 vertical. But whenever we have seen the slope, we have seen as 1 vertical to m horizontal. Whenever we have seen the slope is, it is like 1 vertical to m horizontal. And I am using this m value in the equation. So whenever the slope is given to you like this, you convert it first in 1 vertical to m horizontal terms. How I can say, if it is 2 vertical, if I divide it with 2, so it will be 1 vertical. This is 3 horizontal. If I divide this value also with respect to 2, so it will be 3 by 2 times of horizontal. Or I can say the slope is 1 vertical to 1.5 horizontal. Or I can say m value is nothing but 1.5. This m value is nothing but 1.5. If this m value is 1.5, can I say that this particular dimension, it is going to be equal to, m times of y, and this dimension is also m times of y, and this is nothing but your b value, right? So what is the top width? I'll just write. Now the top width, I can say it is b plus 2 times of my. I'll just take this 2 on this side. It is equal to 2 under root of 1 plus m square, 2y under root of 1 plus m square, right? We need to find out the relation between this b and y. Clear? So then we can eliminate this particular b from that particular equation. As we know, we need to find out the depth of flow, right? Now, can I say this b value, it will be equal to nothing but 2y under root of 1 plus m square. If I take this 2y, 2 times of my on this side, and 2y if I take common, it will be minus m. So it is under root of 1 plus m square minus m. This is the particular b value. So we got this b value in terms of this particular dimension, right? Now, to use the Manning's equation, we need to find out the area of flow, wetted area, this particular area. Now we know that this particular area is nothing but half sum of parallel side, that is this b value, plus this top width, that is b plus 2y, or I'll directly write this area will be what? This will be b plus my into y. B plus my into y. Yes or no? This is what we have discussed previously also when we have calculated the channel geometries. Right? Now, try to see. I'll just replace this particular b value in terms of this y. So it is nothing but 2y under root of 1 plus m square minus m. This value is your b plus my and whole multiply by y. Clear? So if I correct this, what will be the area? This area is going to be, if I take y common in this particular equation, so from here I can take y, from here I can take y. Clear? So area, it will be equal to what? Your area, it is going to be equal to y square under root of 2 into 1 plus m square minus m, right? Just try to see, you'll get this area as, now this is the area for your most efficient channel. This is the area for your most efficient channel. Clear? R value we know, R value, even if the side slope is constant, right? In that case also this R is going to be equal to y by 2 only. This is going to be y by 2 only, right? If I put the values here, it will be y square into, this is not root, this is 2, right? So it is 2 into under root of 1 plus, what will be m value? It is 1.5 square minus 1.5. Clear? Now I can use the Manning's equation, Q is equal to 1 upon n A r to the power 2 by 3 s naught to the power 1 by 2. Discharge is given to me. Discharge is 25 and side slope is 0.004. And side slope is 0.004. This value is 25, 1 upon n. N value is 0.017. Area value we have calculated, that is y square into this particular value, 2 into under root of 1 plus 1.5 square minus 1.5. Clear? Into r to the power 2 by 3 y by 2 to the power 2 by 3 into s naught to the power 1 by 2. What was the value of s naught? S naught value is 0.0004. 0.0004 to the power 1 by 2. Just calculate the y value from here. This is the only unknown. Calculate the y value from here. Yeah, thank you, Prateek sir. Prateek sir, from our civil engineering department, they are also going to deal the structural analysis, right? So the updates will be given to you in the description only. So from there also you can see the schedules, right? So Prateek sir will deal with the structural analysis. You should attend those lectures. That will be very beneficial for you, right? Now, tell me the discharge first. Tell me the discharge value. Tell me the discharge value. Sorry, tell me this depth value. Depth of flow we need to calculate. Discharge is given. Now this particular equation we have converted in the terms of this particular depth of flow. Can you tell me the value of discharge? Sorry, can you tell me the value of this depth? Tell me. Give me the value of this y. Give me the value of y. So, if you solve this particular equation, you are going to get 2.83 meter. This depth will be 2.83 meter. Just let me know if you got the same answer or not. Yes, Prashant, it will be 2.83 meter, right? Very good. Clear? So this is the depth of flow. So your correct answer will be what? Your correct answer will be 2.83 meter. Right? So what we have learned from this particular question, we have learned that there can be a slope given in this particular term. So how to calculate the m value? That is now known to us, right? Now if the parameters like efficient channel is given, so in that particular case, examiner will make two unknowns, right? Whenever there will be a condition of most efficient channel, we know that we will get a relation between the depth of flow and the width of flow. Clear? So in that particular case, examiner generally keep both the things unknown. if you know those conditions, you will be able to find out a relation between this depth and width. Clear? And accordingly, you can proceed with your question. So from this particular chapter, you can see most of the question, it will be from either Chase's equation or it will be from Manning's equation, right? The only difference will be on the basis of your most efficient and most economical channel. This hydraulic characteristics or the cross-sectional characteristics which we have seen, that they are going to change. I hope it is clear, right? Okay, can you calculate this? Just if you can answer this particular question in next 1 minute. In next 1 minute. Why hydraulic radius is not changing? See, I have told you in the most efficient and most economical channel, there were two conditions, right? In one particular case, if you are not changing the side slope, then only if you will derive those particular equation from that, if t by 2 it is equal to the length of your side slope, from that also you will get that the r value is y by 2. I have given you the direct relation if you remember. If you remember this particular case, if you remember the most efficient trapezoidal channel, right? So I have told you that if the channel slope is not variable, we have seen the two type of condition. One is r is equal to y by 2, right? So this r is equal to y by 2, it will be in this case also and it will be in this case also. Clear? This is the direct result which I have given to you. Clear? Otherwise, this particular r by 2, it can be derived from this particular case only. Clear this thing? So I have used that particular directly result, as I have already told you that this r is going to be y by 2 for this most efficient trapezoidal channel. I hope it is clear. Right? This is a derived relation. It is not like that this particular, for this particular it will be there. We have made the discharge to be maximum and you can say we have made the wetted parameter to be minimum. If you will make the wetted parameter to be minimum, in that particular case your r is going to be equal to y by 2. Clear? Now again we will move to our question. Now Prashant, try to answer this particular question in next 1 minute. A very easy question. If whatever we have discussed till now, if you have your full focus here, you will be able to answer this particular question. Try to see. Even by using your pen, you will be able to find out. Try to see. Now, it is saying that if a water is flowing at a same depth in the most efficient rectangular channel and most efficient trapezoidal section, then the ratio of hydraulic radius of trapezoidal to that of rectangular channel is. So you need to find out the hydraulic radius ratio R of trapezoidal channel and hydraulic radius for your rectangular channel. Both are having same depth of flow. Yeah, Abhishek. Good evening, Abhishek. Try to find out this. Yes, it is going to be equal to 1. Why? As we know, for most economical trapezoidal channel, this R value it is going to be equal to y by 2. For most efficient rectangular channel also, it is going to be equal to y by 2. So this ratio will be what? This ratio will be 1. This ratio will be 1. I hope it is clear. Right. So these are some type of questions which can be framed from this uniform flow. Now we'll move to our next part, that is a non-uniform flow. Non-uniform flow. Now try to see these two figures. Here you can see this is particularly a prismatic channel. In that prismatic channel, there is a width contraction in this particular part. So this was the width, initially this was the width, and at this particular point you can see there is a contraction in width. there is a contraction in width. Here also you can see this is the base of the channel, and here you have seen there is a sudden drop in the channel bottom. There is a sudden drop in channel bottom. So whenever there is a sudden drop or rise in the channel bottom, or if there is any contraction along this width, your flow, it is going to change from uniform flow to non-uniform flow. Your flow, it is going to change from uniform flow to non-uniform flow. Clear? Now, in these particular cases, we need to discuss that what are the different parameters related to these things. How the energies are going to change when this particular, there will be a drop in this particular channel, or there will be a rise in this particular channel bottom, right? Also, we are going to see when there will be a contraction, how your discharge per unit width going to change. Clear? It means we need to see that if this particular contraction will be there, there may be the change in energy. There may be the change in energy, right? So we need to see that how this depth is changing. We need to see how this depth is changing with change in these contraction values, right? So what is this particular case? There is a contraction in width of the channel, there is a contraction or there is an expansion in this particular depth of this particular channel. Due to this, the depth of flow, it is going to change. Due to this, the depth of flow, it is going to change, right? So we know that this depth of flow, it is a hydraulic property of our open channel flow. So we need to find out what are the variation in this particular depth. Clear? How we need to find out? We need to see the variation in energy with respect to, or how this energy is changing from one section to another section when there is a width contraction or when there is a contraction in your height of the channel. Clear? Now, which energy we are going to deal? We know that at any particular section, the total energy, it is given by your datum head plus your hydraulic head plus your kinetic head, right? This is the total energy. But if we consider the energy with respect to this channel bottom, or you can say if I assume my datum line at this particular channel bottom surface, the energy we will calculate, it will be nothing but our specific energy. So there is a particular energy which we have defined with respect to the datum line, it as a channel bottom. Clear? So we can say that the specific energy E, it is nothing but this Z value, we have made it to 0, as we have assumed that this datum line is nothing but here. This datum line is nothing but here, right? So what will be our energy? Our energy is going to be equal to y plus v square upon 2g. Y plus v square upon 2g. Clear? What is this? V is the velocity at this particular section, right? I can also write this particular equation in terms of discharge. So it will be where q square upon 2 into g. If I assume this channel to be rectangular, can I say this? Q by area will be equal to b into y square. B into y square. Clear? Now this q square by b square, this discharge by width, we call it as a discharge per unit width. This is nothing but your discharge per unit width. Your discharge per unit width. Clear? So this particular term is nothing but your small q value. It's a square. So can I say that the energy at particular section, it is equal to y plus q square upon 2gy square? Yes or no? Can I say this particular thing? Yeah, thank you, Sandeep sir. Right? So can I say that this specific energy, this is given by y plus q square upon 2gy square. Now I want to see that how this depth of flow, it is changing when there will be change in the specific energy. Also I want to see how this depth of flow, it is going to change when there will be a change in this discharge per unit width. Clear? So for this, I can see that this E, it is directly proportional to y, and E is also inversely proportional to y square. So first, if I keep this discharge to be constant, remember there are two variables on which this depth of flow it is dependent. It depends upon this E value, and there is a discharge value Q. Clear? So first I have kept this Q value to be constant, and I am seeing the variation of this depth with respect to this specific energy. Clear? So from this graph, it is clear that here on the x-axis there is a specific energy, on y-axis there is a depth of flow. If you remember, here E is directly proportional to y. So can I say this particular yellow line, it is representing that E is directly proportional to y, this yellow line. Clear? This yellow line mainly represents your potential energy. This line mainly represents your potential energy, right? Second is, if I see from here, E is inversely proportional to y square also. So also E is inversely proportional to y square. So this is particularly the curve for E is inversely proportional to y square. This red curve, it represents your kinetic energy, right? So if I combine these two, it is going to represent that particular equation. So by combining these two curves, I got this final curve. Right? Now this particular curve, it is representing how the depth of flow it is going to change with change in your specific energy. Yes, correct. Clear? Now try to see. Let's suppose initially in any particular channel, this was the specific energy, right? I'll draw this channel. So let's suppose in this particular channel, initially the flow is uniform. If the flow is uniform, it means at this particular section number 1, if the depth is y, at this particular section number 2, also the depth will be y. Yes or no? In that case, velocity will also be same. In that particular case, you can say your energy or specific energy is going to remain constant. But what if I increase? The base of this particular channel, right? If there will be any rise in this base of this particular channel, will there be any change in specific energy? Let's see. At this particular case, let's suppose this is the depth of flow and this is your energy line, right? So this is nothing but my specific energy. Initially this was the specific energy at this location also, but when you have increased this particular surface and when there is a rise in this particular surface, let's suppose this is delta Z, right? Now the specific energy at this particular location, it is going to reduce. Now this is your E value at this particular surface. So I'll say this is the E1, this is E2. So it means with the rise of this particular floor, your specific energy value it is going to reduce. Clear? Now let's suppose this particular line, it represents your E1 value. What happens when you reduce the energy? In this particular case, energy get reduced. This is your particular E2 value. This is particularly E2 value. So from E1, the energy is now reduced to E2. Why this energy get reduced? As you have raised the base of this particular channel. Clear this thing? Now try to see. If you'll keep on increasing this particular base, your energy is going to shift on this direction. And there will be one case. There will be one particular height of this particular rise, right? Generally we call this particular rise as a hump. So there will be a height of this particular hump for this for which our energy is going to be minimum, for which our specific energy it is going to be minimum. Now if you'll rise this particular hump, for that particular value, there is no discharge, no depth available. There is no depth available. It means for a constant discharge value, this curve is for a constant discharge. If you need to keep the discharge value constant, there is no depth available for this particular specific energy. It means this particular condition, it cannot occur. This particular case, when our energy is minimum, this particular case we call it as a critical condition, right? So at that particular case, we can say that the flow will get choked, and this is your condition for critical condition. So here it is critical condition. It is critical condition, and the depth of flow at this particular point, it is going to be your critical depth, and the depth of flow at this particular point, it is going to be your critical depth. So this is your critical depth. Let's say it is YC value. And the flow at this particular point, it is going to be critical flow. If you remember, we have discussed based on the Froude's number, the flow can be supercritical, subcritical and critical, right? So at this particular case, your flow is going to, if this condition is going to be critical condition, and the flow at this particular point, it will be your critical flow. I hope it is clear. Now try to see. We have seen that if Froude's number is greater than 1, what was the Froude's number? Froude's number was your V upon under root of GD. If Froude's number is increasing, let's suppose at this particular point when the condition is critical, the Froude's number was 1. If Froude's number is increasing, can I say that the velocity value is increasing? Now for a constant discharge, if the velocity is increasing, it means the area is decreasing. Now the width of the channel is constant. Width you cannot change. It means there will be decrease in the depth of flow. So if at the critical point, if the depth is YC, in supercritical flow, the depth it is going to be less than your critical depth. It means at this particular point, if I just remove this particular thing, right, I hope it is clear. So let's suppose it is your critical point. If it is a critical condition, so below this critical condition, your flow will be what? Your flow will be supercritical. It will be supercritical. Clear? It means for supercritical flow, your depth of flow it is going to be less than the critical depth. And the flow above this particular line or above critical line, it is going to be subcritical. It is going to be your subcritical flow. Here it is going to be subcritical. Clear? Now try to see the beauty. When you are increasing this particular, or when you are raising this particular floor, can you tell me what will be the change in the depth of flow? It is going to increase or it is going to decrease? If I raise this particular channel bottom, with respect to this section number 1, here at section number 2, the depth of flow it is going to increase or it is going to decrease? Can you tell me? If it is going to increase or if it is going to decrease? Anyone? I'll again repeat the question. With respect to section 1, if I have raised the base of this particular channel, can you tell me the depth at this particular section number 2, it is going to increase or it is going to decrease? Now try to see the beauty, right? It will depend upon what is the type of flow. Which is occurring in this particular channel. It will be decrease. Let's see, it can increase or it can decrease depending upon the type of flow, right? See here, initially the energy was even, Initially the energy was E1. Here there was the energy. Now the energy is E2. If you have increased this, the energy is E2. If the flow is subcritical, when the energy changes from E1 to E2, you can see that there is a decrease in depth. Right? But if the flow is supercritical, here you can see, initially this was the depth, and now if the energy get reduced, this is your depth. So now it get increased. Right? So whenever the question is asked that due to the creation of hump or due to the rise of the channel bottom, your depth of flow at that particular section, it will increase or decrease. It will depend upon if the flow is subcritical or if it is supercritical. Is this clear? Just let me know if it is clear or not. Just tell me. Is this clear to you? Yes? Prashant? Is that clear? Right? So it will depend upon what is the type of flow. So you have to first define that what is the type of flow. How you can define the type of flow? Based on the Froude's number. So if you calculate the Froude number, if it is equal to 1, it is the critical. If Froude number is greater than 1, it will be supercritical. And if Froude's number is less than 1, it is going to be your subcritical flow. Clear? Right? Now, this is particularly the variation when there is a variation of specific energy. Right? Now if you try to find out how okay बेटा, अगर इस पर्टिकुलर केस में अगर हम देखें, राइट, अगर ये सेक्शन हम देखें तो क्या हमने ये डिफाइन किया था दैट इस पर्टिकुलर पॉइंट पे आपके पास फ्लो होगा क्रिटिकल, इस पॉइंट पे आपके पास फ्लो होगा क्रिटिकल, राइट. अब फ्राउड नंबर हमने डिफाइन किया दैट फ्राउड नंबर इज v अपॉन अंडर रूट ऑफ जी डी. अगर अभी क्रिटिकल केस है तो फ्राउड नंबर 1 के इक्वल है. अगर फ्राउड नंबर की वैल्यू ग्रेटर देन 1 होती है, इसका मतलब वेलोसिटी इंक्रीज कर रही है क्या? अगर डिस्चार्ज को कांस्टेंट रखें, तो कैन आई से दैट माय डेप्थ इट इज डिक्रीजिंग, और डेप्थ ऑफ फ्लो आपके पास क्रिटिकल डेप्थ से कम होगा. तो जब भी इसके नीचे अगर आप देखोगे क्रिटिकल डेप्थ से नीचे, दिस इज योर वाईसी वैल्यू, तो वाईसी वैल्यू के नीचे आपके पास कौन से कंडीशन आएगा? सुपर क्रिटिकल. और वाईसी वैल्यू के ऊपर आपके पास जो कंडीशन आएगी दैट विल बी सब क्रिटिकल. क्लियर है? तो जब आपके पास एनर्जी चेंज हुई थी फ्रॉम E1 टू E2, when there is a change in energy from E1 to E2, for subcritical case depth of flow क्या हुआ है? There is a decrease in depth of flow, whereas in this particular case there is rise in the flow depth. I hope it is clear now. तो ये डिपेंड करेगा आपके पास सुपर क्रिटिकल फ्लो है या फिर सब क्रिटिकल फ्लो है. देन ओनली यू कैन डिसाइड दैट द डेप्थ ऑफ फ्लो इट इज गोइंग टू इंक्रीज और डिक्रीज ओवर अ हम्प. क्लियर? सो हियर वी हैव सीन द वेरिएशन ऑफ योर एनर्जी एंड द डेप्थ. क्लियर? या ओके अभिषेक. नाउ वी आर गोइंग टू सी द if we take the energy to be constant, if I assume the energy to be constant, right, we have seen the previous relation here. So we have seen the variation of energy and variation of depth. If I keep now this energy constant and I want to see the variation between this depth and discharge per unit width, so this is the variation of your discharge per unit width and the depth of flow. Again, now in which case this particular condition is used. Let's suppose this particular is your channel. Now this is the top view of channel. ये आपके पास channel का top view है. Clear? At this particular case, this is your prismatic channel. At this particular case, let's suppose the depth of flow. I'll also draw the side view. तो side view भी आपके लिए draw कर रहा हूँ. Let's suppose this is the depth of flow. Clear? So this is the side view of a rectangular channel, right? And this is the top view of a rectangular channel. Clear? So in top view, you will see this width of the flow. आपको इस channel का width दिखेगा क्या? And in side view, you will see the depth of flow. You will see the depth of flow. Clear? Initially, let's suppose I assume that this particular flow, it is nothing but your uniform flow. It means at this particular point the depth is y. At this particular point also the depth is y. Clear? But let's suppose now we have reduced the width at this particular point. If we reduce the width at this particular point, if I reduce the width at this particular point, clear? Now let's suppose this is the new width. If I have reduced the width at this particular point, right? If the discharge through this particular channel, it is Q. So here my discharge per unit width will be Q divided by this particular B value. Now let's suppose the next width, it is equal to B2. So now at this particular point, the Q value will be different. Q2 will be your discharge divided by B2. It means there is change in this particular discharge per unit width. Now when there will be this width contraction, again there will be change in the depth of flow. Again there will be change in the depth of flow. Clear? Yeah, this Q, if we are reducing this B2 value, your discharge per unit width, it is going to increase. So let's suppose initially this was the Q value. Initially this was the Q value. When you have reduced the width, yeah, thank you Vijay Lakshmi. When you have reduced this particular width, your discharge value it is going to increase. Yes or no? So your discharge value or discharge per unit value, it is going to increase, but it can increase up to this particular maximum value. It can increase up to this particular maximum discharge value. After that, if you'll keep on decreasing this width, there will be a particular width value, after which if you'll reduce this particular width, and to keep the specific energy constant, here what is constant? Here E is constant. So for a specific constant, for a particular specific value, specific energy value, right, you cannot reduce this width further, as there is no particular depth of flow corresponding to this discharge. Here at this particular discharge per unit width, there is no particular depth of flow, right? It means again at this particular point there will be a choking condition. Again at this particular point there will be a choking condition, and you will say that this particular condition is nothing but your critical condition. Right? And the depth of flow corresponding to this critical condition, that is your critical depth. I know that above this particular it will be your subcritical flow, and below this it will be a supercritical flow. Yes or no? Now can you tell me, when you have reduced the width of the channel, the depth of flow at this section number 2, it is going to increase or decrease with respect to this section number 1? Can you tell me? If you have reduced the width of this particular channel, the depth of flow at this particular section, it is going to increase or it is going to decrease with respect to this section number 1? Tell me. It is going to increase or it is going to decrease? Can you tell me? Just answer. Again, it will depend upon what is the type of flow, right? So when you are reducing the width, this discharge per unit width, it is keep on increasing. So initially, let's suppose it was at this particular point. When you have reduced the width, this particular discharge per unit width, it reaches to this particular value, right? If the flow is subcritical, we know initially this was the depth, now this is the depth. So there will be decrease in the depth of flow. But if the flow is supercritical, you can see here, initially this was the depth, now this is the particular depth when you have reduced the width. So here there is a increase in the depth of flow. There is an increase in the depth of flow. Here we have seen the decrease in depth of flow. Here we have seen increase in depth of flow, right? So it will depend upon what is the type of flow. Then only you can decide if the depth of flow it is going to increase or decrease. I hope it is clear, right? So this is the particular topic of your channel transition, right? Now, so what we have seen that the critical flow, it will be when the specific energy is minimum. We have seen the curve. When there will be a specific energy, minimum specific energy, we can say that is the critical condition. Second thing is specific force. Although this particular specific energy we have seen in the terms of energy equation, right? If you use the momentum equation at particular critical condition, your specific force it is also going to be minimum. We have seen the specific force value when we have discussed that momentum equation, right? So that particular specific force value it is also going to remain minimum at this particular critical condition. What about the discharge? You will find out that the discharge at this particular condition, critical condition, it will be maximum. Also at critical condition we have defined that the Froude's number it is going to be equal to 1. Froude's number is going to be equal to 1. And the most important condition, that is Q square T upon GA cube, it will be equal to 1. This particular value Q square T upon GA cube, it is nothing but Froude number square. It will be equal to 1, right? So generally this particular expression Q square T upon GA cube we use for the calculation of this critical condition or to analyze this critical condition, right? So this is your generalized equation Q square T upon GA cube, it will be equal to 1. It is nothing but the value of Froude's number square, right? If you will find out the, if you will convert this particular Q square T upon GA cube, you will get this is nothing but a Froude number square, right? So we know the Froude number is 1, this particular value is also 1. But this is your most important equation corresponding to critical flow. I hope it is clear, right? Now at the critical flow or at the critical condition, what will be the depth of flow? What will be the energy? We have direct relation for two types of channel, that is your rectangular channel and your triangular channel. For any other type of channel, you can use that Q square T upon GA cube and you can find out the different parameters, right? So what will be the critical depth if it is a rectangular channel? If it is a rectangular channel having a width is equal to B and depth of flow is Y, at critical condition this depth Y will be Y critical, right? So this Y critical it is given by Q square upon G to the power 1 by 3, right? Here what is Q? This Q is nothing but your discharge per unit width. This Q is nothing but discharge per unit width. Clear? And specific energy it is given by 3 by 2 times of this critical depth. It is 1.5 times of your critical depth, or you can say 3 by 2 times of your critical depth, right? Similarly for triangular channel also we have some expression. We have derived this expression by this equation only, that Q square T upon GA cube, it is equal to 1. So even if you don't remember these equations, right, sometimes it happens that we get confused in these relations. So remember this particular equation. From here also you can get these values. What will be the depth at critical condition? What will be the energy at critical condition, right? So all other channels other than this triangular and rectangular, we generally use this particular equation, right? But as we have derived these relations, we can directly use this, right? If you remember. So if there is a channel, having an apex downward, right, and it is having a depth of flow Y, side slope as 1 vertical to m horizontal, in that case your critical depth it is given by 2q square upon gm square whole to the power 1 by 5. What is this Q? This is the discharge value. What is the M? M is your side slope, right? It is 1 vertical to m horizontal. So this particular horizontal dimension, it is your m value. Clear? Second here, critical specific energy. Critical specific energy, it will be 1.25 times, or you can say 5 by 4 times of your YC. That will be 5 by 4 times of your YC. Clear? So these are the direct results which you can remember. Now based on this particular discussion, try to solve these questions. This is related to your channel transition and the critical flow conditions. So you'll get a definitely one question from this particular topic. Try to see the question and try to find out. Read the question and try to find out. Try to read the question, understand the question, see what are the data given to you and what it is asked. Try to find out. Now let's read. For a given triangular channel of side slope 2 horizontal to 1 vertical, 2 horizontal to 1 vertical, the depth of flow in the channel corresponding to maximum discharge is 0.5 meter. It is 0.5 meter. So your depth of flow, it is given corresponding to maximum discharge. Can I say it is a critical condition? So this is nothing but your YC value is given to you, 0.5 meter. The specific energy corresponding to the given condition is, and you need to find out the specific energy. Let's suppose as it is a critical condition, so you need to find out this EC value. EC value, specific energy at this particular critical condition. How we know that this is a critical condition? As the discharge is maximum, right? We have seen the critical flow conditions, right? Now this is the particular channel given to you, right? This is also open channel, as this particular surface, it is open to atmosphere or it is having a constant pressure value, right? This base width is given to you 3 meter. Clear? Now try to see the triangular channel for which we have seen the standard values, that was having an apex downward. That was having an apex downward. It means those relations you cannot directly use here. Clear? So in that particular case, if we cannot use those relations directly, what we have to use? We have to use that particular critical flow condition. We know for critical flow, that Q square T upon GAQ value, it is going to be equal to 1. It is going to be equal to 1, right? So from here you need to find out this EC value. How you will find out this EC value? Try to see how you can find out the EC value. Now EC is nothing but your critical energy, right? So I know that critical energy is nothing but Y plus V square upon 2G. Y plus V square upon 2G. Yes or no? So it means I need the value of depth of flow, that is given to me. I need velocity value. The only value which I need for calculation of this critical energy or energy at this particular section is this velocity value. Now try to see how we can find out the velocity value from this particular equation. Right? Now can I say this Q square upon A square is nothing but velocity square? As I know that Q is equal to area into velocity. So velocity will be equal to Q by A, or velocity square, it will be equal to Q square upon A square. It will be Q square upon A square, right? So I got that. From here I can calculate this velocity value or V square value. If V square value is known to me, I can find out the energy here. Now try to see. For this discharge Q square upon A square, I will need the top width. So first try to find out this top width. Right? It is given as the depth of flow is here 0.5 meter. This is 0.5. Clear? So the slope is given to you that one vertical to two horizontal. If you are moving one in vertical direction, you have to move two in horizontal direction to make this particular slope, right? So we have moved 0.5 in vertical direction. It means we have moved to 1 in this horizontal direction. Similarly, this dimension will be 1. If this is 1, this is 1, it means this particular dimension will also be 1. At this total dimension, it is 3. So can I say that this particular top width, it is nothing but equal to 1 meter? This top width is nothing but equal to 1 meter. So I know the top width value, right? So from here I can calculate, right? So Q square T for critical flow, I know that Q square T upon GAQ, it is equal to 1. This Q square upon A square, it will be equal to what? This A into G by T. Top width we have already calculated. Top width is nothing but equal to 1. What will be the area we can see? What will be the area of flow? Can you tell me? This area of flow, this is nothing but a trapezoid. This particular part, it is nothing but a trapezoid. It will be half sum of parallel sides into this length. This dimension is 1 meter. This dimension is 3 meter. And distance between the parallel side, it is 0.5 meter. Right? So I can calculate the area. What is this area? Area is equal to half sum of parallel sides. Top width is 1 and the bottom width is 3 and the distance between these two is 0.5. So it is 3 plus 1, 4, 4 by 2 and 0.5, it is going to be also equal to 1. So 1 meter square. So now I can calculate this particular value. It is nothing but A is your 1 value into G by top width is also 1. So it is nothing but equal to G. This Q square upon A square, this is nothing but value of your velocity square. This is the value of your velocity square. Clear? Now I can calculate the energy at section number 2. For E is equal to Y plus V square upon 2G. Right? Y value is given to me 0.5 plus velocity value we have calculated, velocity square value, it is equal to G upon 2G. This G get cancel out. It will be 1 by 2, that is 0.5. So 0.5 plus 0.5, it will be 1 meter. It will be 1 meter. So the energy at this particular condition, it is going to be what? It is going to be your 1 meter. Right? We need to find out the specific energy in the terms of meter only. So it will be equal to 1 meter. I hope this particular question is clear. Let me know if this particular question is clear to you or not. I hope this question is clear. Right? Okay. Now, let's move to our next question. Try to read the question and try to figure out what we need to calculate and how we can calculate this particular question. Right? I hope it is visible. So it is consider a uniform water flow. Consider uniform water flow in a wide rectangular channel made unfinished concrete with Manning's roughness coefficient. That is nothing but a material is given to you, right? And here the Manning's roughness coefficient is given. Clear? Laid on a slope, not side slope, the bottom slope, channel bottom slope is given to you with a flow depth. Flow depth is given to you 2.947. Now the water flows over a 15 centimeter high bump. 15 centimeter high bump. If the flow over the bump is exactly critical, determine the flow depth over the bump. Clear? So it is a condition like this. There is a channel and this particular channel, there is a bump. Bump is nothing but a rise, and this rise is given to you that having a 15 centimeter, or you can say 0.15 meter. It is 0.15 meter. Clear? There will be a flow of water in this. This depth of flow, it can increase or decrease depending upon the type of flow, right? Now, it is given that initially the depth was 2.947. When you have created the bump, obviously there will be change in this particular depth. So you need to find out this depth. You need to find out this depth, right? And this bump, you have increased up to a height. You have increased this particular bump up to a height such that there is a critical condition at this particular section. There is a critical condition at this particular section that is given to you, right? You need to find out that Y2 value now. Tell me how you can proceed. Tell me how you can proceed. Okay, first tell me, when you are increasing the base of this particular channel, your specific energy, it is going to change or it is going to remain constant? It is going to change or it is going to remain constant? Can you tell me? We have discussed this thing. Tell me. We have already discussed this thing. If we are increasing the base of this channel, the energy at section number 1 and section number 2, it will be same or it will be different? We know that at section number 1 and section number 2, the energies are going to change but your discharge will remain constant. Your discharge will remain constant, right? So we have seen a relation between the specific energy and depth of flow. From there, we can proceed with this particular question, right? Now try to figure out. This is the particular case. This is the particular case, right? So the dimensions related to this particular case, when there was no bump, it is given to you. Now it is asking that when you have introduced a bump of 0.15 meter, what will be this depth of flow? This Y1 value was given to you. What was the value? This value is 2.947. This value is 2.947 meter. Clear? What are the other values given to you? Other values are given as slope, Manning's coefficient. It means if the slope is known to me, Manning's coefficient is known to me. This Y1 value is known to me. Can I calculate what will be the velocity at this point? If velocity is known to me, I can calculate what will be the energy at this particular point. I can calculate what will be the energy at this particular point at section number 1. As specific energy, for specific energy we need this Y1 value and the velocity at this particular section. Yes or no? Try to figure out. So channel slope, it is roughness coefficient is 0.014. So n value is given to you 0.014. Side slope of channel is given to you 0.0022. 0.0022. Can you calculate the velocity at section number 1? Can you calculate the velocity at section number 1? So see, when you are keep on increasing this hump, your specific energy value, it is going to decrease. Your specific energy value, it is going to decrease. When specific energy will keep on decreasing, there will be a condition when it will reach to this particular point. There will be a case when it will reach to this particular point. At this particular point, your flow will be critical and the energy at this particular will be critical, right? So this will be nothing but your critical case. So I can say this is nothing but YC, right? This is a rectangular channel. So I can say YC is nothing but Q square upon G to the power 1 by 3. Can I say YC is equal to Q square upon G to the power 1 by 3? Yes or no? Or I can say, I also know that this EC value or the energy at this particular section, it will be E critical, that is given by 3 by 2 times of YC. 3 by 2 times of YC. This is also known to us, right? We know that the total energy at section 1 and total energy at section number 2, it is going to remain constant, as there is no loss of energy we have considered, right? So at section number 1, the energy is, if the total energy is even, here also the total energy should remain same. Total energy should remain same, right? So if I say, let's suppose this is your energy line, right? So this is the energy at section number 1, E1. What is the total energy at section number 2? The total energy at section number 2, it is E2, or you can say EC value plus this Z value, right? So I can say the total energy at section number 1 and total energy at section number 2, it will be same. What will be total energy here? If I assume this as a datum, so what will be it? It will be E1 value, that will be nothing but equal to E2 plus this Z value. Or I know that at section number 2 there is a critical condition, right? So this particular E2 value will be nothing but E critical plus Z value. I can calculate this E1. What will be this E1 value? This will be Y1 plus V1 square upon 2G. Y1 plus V1 square upon 2G, right? So we need to calculate this V1 first. V1 we can calculate using this Manning's equation for section number 1, right? How we can calculate? V1, it will be nothing but 1 upon N. Yes. Or critical condition is also there, right? If there is a critical condition, that also we can use. Okay, but just first calculate that V1 value. One upon N, R to the power 2 by 3, S0 to the 1 by 2. It is equal to 1 upon N into R. Channel bottom is given to it. Okay, base of the channel is not given, right? So we have to use, okay. One more important part which is given here is this wide rectangular channel. Very important word. Wide rectangular channel. Clear? Now what is the meaning of wide rectangular channel? Try to understand. This wide rectangular channel, it means that particular channel in the depth of flow, in which the depth of flow, it is very much less than the width of flow. If this y, it is very much less than this width, if the depth of flow in this particular channel, it is very less than this particular width, we call it as a wide rectangular channel. Now, why this wide rectangular channel is given to you? As if this y is very much less than b, if I say for a rectangular channel, what will be the r value? Hydraulic radius value. If there is a channel, let's say, I'll just make it here, for a wide rectangular channel, wide rectangle, for a wide rectangular channel, if we see, this is particularly your channel, right? And it is having this depth of flow as y, and width of flow is b, and width of flow is b. Now if I assume that this b, it is very much greater than y, now for this particular section, if I calculate the value of r, we know it is going to be equal to area upon wetted parameter. What will be the area of this channel? Area of this channel, it is going to be equal to b into y. What will be the wetted parameter? Wetted parameter, it is going to be equal to b plus, this is y, this is y. So can I say b plus 2y? Can I say b plus 2y? As this 2y value, as this y value is very much less than this b, this 2y value we can neglect, right? It will be having a very less change. Let's suppose b is 10 meter and y is your 0.05 meter, right? So you can see that there will be hardly any change in this particular value when you will add this 2y in this particular B. This particular case, it can only arise when there is a wide rectangular channel. Clear? So it means I can neglect this particular value. So it is nothing but equal to B into y by B. If I cancel this B by B, so I can say for a wide rectangular channel, what will be R value? Your R value it is going to be equal to y. Your R value it is going to be equal to y, right? So remember this particular thing. When there is a wide rectangular channel, your hydraulic radius value it will be nothing but equal to y for a rectangular channel. Clear? So here now, as a wide rectangular channel is given to me, can I replace this R value with respect to y? As I am calculating V1, I will write it as y1 to the power 2 by 3 into S0 to the power 1 by 2. Now n value is given to me. What is n value? Our n value is 0.014, 1 upon 0.014, right? Okay, 0.014, and S0 value is 0.0022. Depth of flow was also given, right? Depth of flow is given to us, that 2.947. 2.947 to the power 2 by 3 into S0 value 0.0022 to the power 1 by 2. Can you tell me what will be the value of V1? What is the value of Vn you are getting? Just calculate this value and let me know. Just calculate this value and let me know. What is the value you are getting by calculating the V1? The trick was this wide rectangular channel word, right? Very important. Your R will be equal to, hydraulic radius value will be equal to y if there is a wide rectangular channel. Clear? It is 6.88. It is equal to 6.88 meter per second. V1 is 6.88 meter per second. Clear? Now I calculate the energy at section number 1. E1 will be equal to y1 plus V1 square upon 2g. Y1 value is known to me, 2.947 plus velocity value is known to me, 6.88 square upon 2 into g, 9.81. Just solve this value and give me the value of specific energy at section number 1. Prashant, just calculate this value and give me the value of specific energy at section number 1. What is the value? What is the value you are getting? 5.364. It is 5.364 meter, right? Now try to see this E1 value. It is 5.364. This E1 value, it is nothing but 5.364. It will be equal to E critical plus Z value, it is known to us. Z value is given as 0.15. 0.15. Clear? So what will be the E critical value? This E critical is nothing but the energy at section number 2. What is the E critical value? What will be the E critical value? It is going to be equal to 5. Tell me Prashant, what will be E critical value from this particular relation? We know E1 is equal to 5.364 we have calculated. It will be 0.15 you have to minus. It will be 5.364 minus 0.15. It will be 5.21. It will be 5.21 meters, right? What 5.25 meters, right? We need to calculate the flow over the bump. We we need this Y2 value or Y critical value. If E critical is known to me, I know for a rectangular channel, E critical is equal to nothing but 1.5 of YC. So YC I can calculate, right? YC we can calculate, that will be 5.21 by 1.5 by 1.5. What will be the value? We got the EC value. We know that at section number 2 there is a critical condition, so the depth will also be critical depth, right? We know for a rectangular channel critical depth or critical energy is nothing but 1.5 of YC. Divide करना है, 1.21 divided by 1.5, it is 3.47. It is 3.47 meter. It is 3.47 meter, right? So yes, your option number B will be correct, right? 3.48 meter. 3.48 meter. I hope it is clear, right? So whenever there will be a rise in bump, you know that there is going to be change in specific energy, but the total energy will remain same, the discharge will remain same. Clear? So what are the things you can compare? You can compare total energy, or either you can compare the discharge at these two particular cases. I hope it is clear, right? Now let's try to see one question from your width contraction. Try to see one question from width contraction. See the question and try to just read the question and try to see what you need to find out. What is the data given to you and what you can calculate. Just read the question. Just read the question. It is given that a bridge is planned on a 50-meter wide rectangular channel. So there is a wide rectangular channel having a 50 meter. Let's see where the students get confused. This 50-meter wide, it is written that a rectangular channel having a 50-meter width, right? It does not mean it is also a wide rectangular channel. Clear? So it is 50-meter wide rectangular channel carrying a flow of 200 meter cube per second. 200 meter cube per second. This is the discharge value at a flow depth of 4 meter. For reducing the length of the bridge, what is the minimum channel width such that the upstream water level is not influenced for this discharge? Such that the flow depth at the upstream, it will not get changed. Now first try to understand the question. What question says? Let's suppose if I draw the top view of a channel. I am drawing this the top view, right? You are seeing a rectangular channel from the top. So you will see the boundaries of this channel. It means this is the width. It means this is the width of the channel, right? Now you want to create one bridge to cross this particular channel. That bridge, it will be along this particular width, yes or no, or across this particular channel, right? So let's suppose this is the bridge. What will be the length of bridge? The bridge length, it should be equal to or greater than this particular width of the channel, yes or no? Now you want to reduce the length of this particular bridge. So for that, what you have done? You have reduced the width of this particular channel. As the length of the bridge will decrease, it means it will be more economical, right? So for what you have done? You have contracted the width. You have contracted the width. Let's suppose now you have contracted this width up to a value of BM, right? Up to a value of BM. So you are keep on reducing. There will be one condition. At which the flow will get choked. We have seen that when you are keep on decreasing the width, your discharge per unit width, it will keep on increasing, right? Here you can see when you are decreasing the width, initially this was the width, now you have decreased the width. So you know that your discharge per unit width, it will keep on increasing, and at a particular value of discharge, your flow, it is going to be get choked. Thank you, Amit Goyal. Right? So at this particular point, you know that your discharge, it is going to be get choked. If you will reduce the width after that, what will happen? You know that there is no depth corresponding to this particular discharge value, right? But this particular case, it is for any particular specific energy. If you will change the specific energy, definitely there will be some discharge. Definitely there will be some depth corresponding to this discharge value. But when this specific energy will change, it will also alter the flow properties at upstream end. Clear? But in the question, it is said that the upstream water level, it should not alter or it should not get influenced. It means the minimum width which you can provide, it is up to the critical condition. It means again here the condition will be critical condition. Here the energy will be E critical and the depth will be Y critical. But in this particular case, you need to find out what will be this B value, right? What will be the minimum width up to which you can reduce this particular channel width so that one bridge can be constructed over it such that upstream water level, it will not get influenced. How you will proceed with this particular question? Can you let me know how you can proceed with this particular question? In last question, we have seen the depth contraction, right? There will be a rise in this particular floor of the channel. In this particular case, they are reducing the width. How we can approach? Tell me. Okay, first tell me, when you are reducing the width, the specific energy, it is going to remain constant or it is going to change? When you are reducing the width of the channel, your specific energy at section number 1, let's suppose this is the section 1, this is the section 2, it is going to change or it is going to remain same? Tell me. Yes, it will remain constant, right? This is what we have seen. Here there will be change in the discharge per unit width. But your specific energy, that is going to remain constant. So we can compare the specific energy at section 1 and specific energy at section number 2, right? So how we can proceed? We know that in this particular case, specific energy at section number 1, it will be equal to specific energy at section number 2. Also at section number 2, the energy is nothing but E critical, as the critical condition arises at the particular point. What is this? It is the E critical value, right? Now what is the data given to you related to this E1? What is the data given? The data given is, it is having a width of 5 meter and discharge of 200 meter cube per second. So discharge value is given 200 meter cube per second and width is given to you, that is 50 meter. Any other value given? Yes, depth of flow is also given to you when there was no alteration in this the width of the flow. So Y value is also given to you. Y value is given as 4 meter. Y value is given as 4 meter, right? So you can calculate this E1 value. What will be E1? E1 will be Y1 plus Q square upon G into area square, that is B into Y square, and this is Y1. Y1 value is given as 4 meter plus discharge value is nothing but 200. So 200 square divided by G, 9.81 into V value is given to me, that is 50 into Y1 value. What will be this Y1? Y1 will be 4 meter, 4 square. Can you give me the value of this specific energy at section number 1? Just give me the value of specific energy at section number 1. Specific energy at section number 1. Give me the value of specific energy at section number 1. Now, one more relation also. If you see this particular formula, we know that this E1 value is nothing but equal to E critical. For this particular critical case, right, it is 4.1, right, 4.1. Okay. Also try to find out, try to see this particular equation. We can analyze from this, or we can make one direct result from this, right? We know that E1 will be equal to E critical for this particular condition, right? So E1 is, if I write it as E1 only, E critical, I know that for a rectangular channel it is going to be equal to, we know that EC is equal to 1.5 of YC, or I'll write 3/2 times of YC, right? We know that it is nothing but 3/2 times of YC. If I replace this YC, I know for a rectangular channel, this YC is nothing but Q square upon G. To the power 1/3. Q square upon G to the power 1/3, right? Now, this E1 value, it is equal to, I'll just take it as here 2/3, it will be its whole cube. It will be Q square upon G, right? This Q square upon G, I can write it as Q square upon G. Q square upon G. Can I say this Q square upon G, if I know, or I can say it as okay. I can say it as Q square upon G into A square. Q square upon G into A square. We can write this particular formula also like this, right? We need to find out one particular relation. Now this area, it is nothing but Y into B. This is nothing but Y into B for this particular case. So let's suppose this is Y into B square, right? So I need to find out this B value for this particular critical case, right? So what will be this B value? Let's say we have removed, we are considering this critical flow only. So this BM value will be equal to 2/3. BM value will be equal to 27 Q square upon 8G even cube upon 8G even cube, and it will be the BM square value, right? So BM will be under root of 27 Q square upon 8G even cube. Clear? Q will be Q by B. Okay, Q by B. Yes. It will be Q by B. Right? It will be Q square upon BM square. Right? So from here, if I try to find out this BM value into there is G. BM value, what it will be? BM will be this Q square. This is nothing but 3 to the power cube, that is 27, upon this 2 cube, it is nothing but 8 into G into E1 cube, right? So what we will get? We will get a relation as BM is equal to nothing but 27 Q square upon 8G E1 cube and its under root. and its under root, right? So we can also use this particular formula directly, right? So what will be the minimum width of the channel? That will be 27 q square upon 8g even q. Clear? Either we can directly use in this type of questions where we have to calculate the width corresponding to your critical flow. Clear? Now try to see here. We have calculated the E1 value, that is your 4.1. Discharge value is given to me 27 meter cube per second. Now just put the values in this particular case. So I can calculate this Bm is nothing but under root of 27 into Q value is 200, its square, upon 8 into G, that is 9.81. E value we have calculated as 4.1 cube. 4.1 cube. Just give me the value of this particular width. So this is the value of width which you can provide, and this is the minimum width which you can provide. Clear this thing? If you reduce the width below this particular value, the energy at section number 1, it should get changed. If the energy at section number 1 is changing, it means the depth of flow, the velocity at that section number 1, it is going to change, right? And it is given in the question that those particular value, it should be constant or it should not alter, right? Just give me the value, it is 14.13. So Bm value is here 14.13 meter. Let's check if any option is matching or not. So 14.5, right? This is the most appropriate answer, that will be 14.5 meter. So if you reduce this value below this particular 14.13, or you can say just 14.5, what is going to happen? Here the water level at upstream point, it is going to get influenced. Is that clear? If this particular question is clear, we can move to next. Just let me know. So from this particular energy depth relation, these type of questions can be asked, right? Either it will ask for the critical depth or it will ask for the critical energy. Other than that, it can ask for your width contraction and the case of hump, right? So these are the some type of questions which can be which we can figure from this particular topic, right? Now let's move to our next topic. Next topic is our gradually varied flow. Now, whenever there is some obstruction in the channel or whenever there is a change in the slope of the channel bed, your depth of flow, or you can say the flow profile, it is going to change, right? Now, if we are saying that it is a gradually varied flow, what does it mean? It means the depth of flow or the flow properties, they are changing gradually, right? Which flow property we are considering here? The depth of flow. So you know that, let's suppose here the depth of flow is y, and when you have constructed this particular dam, at the upstream of this particular dam, you will see that there is a rise in this depth of flow. There is a rise of depth of flow, right? But this particular rise, it is after traveling a long distance, right? तो अगर आपके साथ लेंथ में जब आप वाटर मूव कर रहा along the length, if there is a variation in the depth, but this variation is gradual, if this variation is gradual, it is going to be your gradually varied flow. Clear? Now here you can see, if let's suppose this is the x direction and depth is y, you can see here that the depth, it is going to increase with respect to this x value. So here the dy by dx, it will be positive. So your depth of flow, if it is increasing with the length, you will say that particular curve, it is a backwater curve. This is a backwater curve. Whereas if you see this particular example, here the channel slope gets changed. Initially this was the slope, now the slope gets changed. Now due to this change in slope, you can see the water profile. So here there is a reduce in the depth of flow. Here there is a reduce in the depth of flow. If this dy by dx you will calculate, it will be now the negative value or it will be less than 0. That particular type of curve, we call it as a drawdown curve, right? It will not be a drawn drop, it will be drawdown curve. it will be a drawdown curve. Clear? Now try to see what type of question examiner can frame. As we know, the depth is changing with respect to x. So how or what will be the change in depth with respect to x? That we need to calculate. Also, try to see when there will be a change in the depth of flow, there will be change in the specific energy also. So your specific energy also going to change with respect to this length. Clear? So there are two formulas for the calculation of how your energy is going to change with respect to the length or with respect to x, we will say here, right? And how this particular depth of flow it is going to change. Let's try to see. We are not going in much detail, but yes, here you can see that the energy change in specific energy with respect to x value, it is nothing but S naught minus SF. What is this S naught value? This S naught value is your channel bottom slope. This is your S naught value, channel bottom slope, and this is your energy grade line, and the slope of this energy grade line is SF. Now remember students, here S naught and SF are now not same. S naught and SF are not same, right? If this would be a uniform flow, we know that S naught and SF would be same. In that case, you have seen that in a uniform flow, we have not considered any change in specific energy with respect to length. We have not seen any change in specific energy with respect to length. So in that case, it was 0. But now, as there is a variation in the flow depth, there is a variation in the flow velocity. So definitely there will be change in the specific energy with respect to x given by S naught minus SF, right? S naught is your channel bottom slope and SF is your energy line slope. Clear? Now, if you need to find out what is the change in the depth, that change in depth, it is given by dy by dx is equal to S naught minus SF 1 minus q square t upon Ga cube, right? So we call these equation as your differential equation for gradually varied flow. Clear? They are generally representing the profile of this flow. Clear? So dy by dx is nothing but S naught minus SF 1 minus q square t upon Ga cube. Also you can write this particular expression in terms of Froude's number. We have seen this particular expression earlier also. This is nothing but your Froude number square. So in terms of Froude number also you can write. Clear? So these are the two type of question which can be asked. Either it will ask for what is the change in energy, or either it will ask for what is the change in this particular depth of flow. Clear? Now as we know, there will be change in depth of flow depending on the type of slope of the channel. Again remember, depending upon the type of slope of the channel, there can be different type of slopes. There can be different type of slopes, and depending upon those slope, your flow profile will be different. Clear? What are the different type of slope that we will see? Clear? Okay, I'll just add one page. Now let's suppose this is the slope of any particular channel, right? This is the slope of any particular channel. Let's suppose it is having a slope of SC. It means I am assuming that this is the particular slope in which if the flow will occur, it will flow at critical depth. So corresponding to critical condition, this is the particular slope. I'll say it as a critical slope. I'll say it as a critical slope. Why I am defining this first critical slope? As with respect to this critical slope, we can define the other slopes. Clear? So this is the particular slope of channel. If you will provide this particular slope, the flow in this particular channel will be critical. Clear? It means this depth will be your critical depth. Now, if the channel slope, it is less than this particular critical depth, in this part, if you see this channel slope, it is less than this channel slope. This particular slope, it will be your mild slope. It will be your mild slope. It means for mild slope, let's suppose if I say SM, for mild slope, it will be less than your critical slope. It will be your less than your critical slope, right? Or sometime we write in the terms of normal slope related to uniform flow, right? or slope related to uniform flow. Let's suppose the slope related to uniform flow is S naught. It means S naught is less than your SC value. S naught is less than your SC value. If the slope is less, it means velocity will be less. If the slope is less, it means velocity will be less. For a constant discharge, it means depth of flow in this particular case will be more. So I can say in the mild slope, the normal depth, it will be greater than the critical depth. The normal depth, it will be greater than the critical depth. Now the question arises, sir, what is this normal depth? This depth, normal depth, it is nothing but a depth corresponding to a uniform flow. If in any particular channel the flow is uniform, then at what particular depth the water will flow, that particular depth is nothing but your uniform flow. This is the depth corresponding to uniform flow. Depth corresponding to uniform flow, right? Uniform flow. Clear? What is this YC? YC is the depth corresponding to your critical flow. Now try to see, if you will increase the slope, greater than this critical, this is going to be your steep slope. This is going to be a steep slope. It means, let's suppose in this particular case the slope is SS, it is greater than your SC value. Or in terms of normal slope corresponding to normal flow, it will be, or uniform flow, you can say S naught will be greater than SC. S naught will be greater than SC. If the slope here is greater than this critical flow, it means here the depth of flow will be less than the critical depth. So what will be the condition? Here YC will be greater than Y naught. Here YC will be greater than Y naught. So remember, for mild slope, Y naught is greater than YC. For steep slope, YC is greater than Y naught. Clear? So these are the three types of slope. One is mild slope, one is critical slope, one is steep slope. There are two slopes also. If the bottom slope, it is equal to 0. If the channel bottom slope, this S naught is nothing but the channel bottom slope. If the channel bottom slope is 0, we will say this particularly is nothing but a horizontal slope. So this is the particularly horizontal slope. This is particularly the horizontal slope, right? And let's suppose the channel slope is like this. The water is flowing in this direction and the channel slope is like this. It means, can we say this particular slope is negative if I am taking this particular slope as positive? So this increase in the slope value along the direction of flow, it will be your negative slope. So this type of slope we call it as a, if this channel bottom slope, if it is negative or less than 0, we can say, if this S naught value here is less than 1, this particular type of slope we call it as an adverse slope. Adverse slope. Clear? So we have seen this S naught is your channel bottom slope, SC is your critical slope. So in this particular case, the slope is S naught is nothing but S critical. So this was the, in this particular channel there is a critical flow. If the channel bottom slope, it is less than your critical slope, it will having a mild slope. And if the channel bottom slope, it is greater than the critical slope, it will be a steep slope. After that, if this channel bottom slope, it is 0, you will say it as a horizontal. And if this particular horizontal slope, if this particular channel bottom slope, it is negative, you will say it is a adverse slope, right? Now, when the water will flow through this, depending upon the actual depth of flow, remember, depending upon the actual depth of flow, there can be different flow profile which can occur in a particular channel. And it will also depend upon what is the type of slope in this particular channel. Clear? So by now we have seen the three depth. One depth is your Y value. In this diagram we can see there is Y value, that is your actual depth of flow. One is your YC, that is critical depth and one is y naught. One is y naught, that is your normal depth, right? Here in this it is mentioned as yn. This y naught and yn, they are same, right? In this particular diagram it is represented as yn. Clear this thing? Now depending upon the location of this actual depth and this critical depth and normal depth, we have different type of flow profiles. We have different type of flow profiles, right? So in steep slope, in critical slope, in mild slope, in horizontal slope, in adverse slope, there can be different cases. Let's suppose if I take the example of steep slope. Clear? I'll just explain for one. For rest of the cases, you can just read, right? So I'll just take the example of steep slope. We know that steep slope, your critical depth, it is going to be greater than your normal depth, right? Now, let's suppose this is the channel. This is your channel. Clear? Let's suppose if I take, this is a steep channel. This is the case of a steep channel, right? It means I am assuming that we know that in a steep case, we have seen that our y critical value, it will be greater than y normal value. So it means this is our critical depth line, this is your normal depth line, right? It means this particular depth, it is nothing but y and normal depth, and this particular depth is your critical depth. Clear? Now try to see what are these yn and yc. If in a channel the flow is occurring at a uniform flow, if in a particular channel the flow is occurring at a uniform flow, it will flow at this particular depth. That is your normal depth, right? If any particular channel, if the flow is occurring, or if in this steep slope, if the flow is occurring at a critical condition, so the depth at that time will be this particular critical depth, at this critical depth line. Clear? But in actual, the flow can be at any particular depth, right? So actual depth can be here, y value can be here, y value can be here, or y value can be here, right? When this y value will be at this line, when this y value, depth of flow will be at this line, you will say it is a critical condition, right? When y value is this particular line, you will say, okay, the water is flowing at uniform flow, right? Or it is, if it is parallel to NDL, you will say that, okay, in this particular channel, the flow is uniform. But in any generalized case, depth of flow can be here, depth of flow can be here, depth of flow can be here. Clear? So, depending upon the depth of flow, we get the different type of profile. So here we will get S1 profile, in this particular case we will get S2 profile, and here in this case we will get S3 profile. Here we will get S3 profile. Now if you see at this particular S1 case, your y is greater than y critical. In this particular case, your y is less than y critical. And in this particular case, your y is again less than y critical. Your y is less than y critical, right? If y is greater than y critical, what we can say? If y is greater than y critical, if it will be a supercritical case or subcritical case, can you tell me? If the depth of flow, it is greater than the critical depth, it will be a supercritical case or subcritical case? Prashant, can you tell me? It will be a supercritical case or subcritical case? We have seen that if the depth of flow it is greater than your critical depth, it will be subcritical, right? So here the flow will be subcritical, and in these two cases it is going to be supercritical. It is going to be supercritical. Or can I say here the Froude's number will be less than 1, and in this case the Froude number will be greater than 1, and here also the Froude number will be greater than 1. Clear? So if you remember, we have seen one relation that dy by dx it is equal to S naught minus SF upon 1 minus Froude number square. Right? So depending upon this Froude number value, depending upon this S naught and SF value, you can tell me that if dy by dx will be positive or negative. If dy by dx is positive, you will say it will form a backwater curve. It will form a backwater curve. And if dy by dx is negative, it will be a drawdown curve. It will be a drawdown curve. Clear? So generally in this particular first part, you will find the flow to be, curve to be your backwater curve. Here it will be a drawdown curve. And again in this particular third case, again it will be a backwater curve. Again it will be a backwater curve. Right? So these are the particular analysis that we need to do from this particular condition. So for every case, I have already prepared this particular chart. Right? So we have seen that the Froude number in the first case, S1 profile, it will be less than 1, subcritical flow. Here it is greater than 1 for S2 profile, and it will be greater than 1 for S3 profile. Right? These are the depth where will be the location of your critical depth, normal depth with respect to your actual depth. Right? So depending upon that, for each and every case or for each and every type of slope, you can do this analysis. I hope it is clear. Right? I have just told you for the steep, same analysis you can do for critical, mild, horizontal and adverse slope. Right? So depending upon this location of the slope or this location of the depth of flow, examiner will ask you in any particular channel which type of profile will get formed. Clear? So whenever you have to decide which type of profile will get formed, you will need to find out these three values: y value, yn value and yc value. Y value, yn value and yc value. Clear? Now try to see. We have seen the relation for yn value. Yn is nothing but this is the depth corresponding to normal flow or uniform flow, depth to uniform flow. Right? It means when the flow is uniform, this will be the depth. And we know that at uniform flow, your S naught will be is equal to SF. And we know that in this particular case, when we use the Manning's equation or Chase's equation, we know Q is equal to 1 upon N A R to the power 2 by 3 S naught to the power 1 by 2. So if you put the S naught value here, we know that this A and R, they are the function of Y. They are the function of Y. So examiner will give you the data like discharge value, it will give you the channel bottom slope. So if you will reuse this particular relation, the Y which you will get from here, it will be nothing but your Y normal value. I hope it is clear. How to calculate YC value? YC value, you know, it is the depth corresponding to critical flow. Depth corresponding to critical flow. Right? If it is the depth corresponding to critical flow, we can use this relation Q square T upon Q square T upon GA cube is equal to 1. These terms will also contain the depth value, right? So when you'll calculate the depth from here, that Y will be nothing but your Y critical. Clear? And for the rectangular channel and triangular channel, we have already seen the final results, right? That YC is equal to Q square upon G to the power 1 by 3 for your rectangular channel, and Q square is equal to, YC is equal to 2Q square upon GM square whole to the power 1 by 5 for your triangular channel, right? So from here you will be able to calculate the YC value. So these two depths are clear. Now third depth which we need to calculate is actual depth. This is your actual depth. So either this actual depth, it can be given to you, or in this particular discharge formula, this particular Y, it is related to your actual gradually varied flow. So if you use Q is equal to 1 upon N into A into R to the power 2 by 3, instead of S0, now you have to use SF value. SF value, as if there is a gradually varied flow, you know that S0 and SF are going to be not going to remain same. So if you will use this SF value, again these two parameters, they are containing the Y value. So from here, if you will calculate the Y, this will be actual depth. So you can calculate Y from here, you can calculate YC from this particular relation, and you can calculate the Y normal from this, right? And based on the combination of these three values, right, or the three depth, you can decide which type of profile can form, right? So this is the particular type of question which generally asked in your exam, right? Try to see the question. Now try to see the question. If there is any doubt, you can ask. Otherwise, you can just go through this particular question. Just try to read the question and try to answer. This is a very simple question. It is saying that in a rectangular channel of 12 meter width and 3.7 meter depth, the water is flowing at a velocity of 1.2 meter per second, right? The channel has a bed slope of 1 in 4000. If the flow of water through the channel is regulated in such a way that the slope of energy line is 0.0004, the rate of change of depth of water in the channel is, and you have to give the answer in the terms of 10 to the power minus 4, right? Always see whatever are the units given to you in these numerical answer type of questions. Also see what are these values, in which terms you need to find out this particular answer, right? So you have to give the answer, multiply by 10 to the power minus 4. So this is asking for a change in the depth of water, change of depth of water in the channel. It means it is nothing but asking for dy by dx value. We have seen a relation for dy by dx. It is nothing but S0 minus SF upon 1 minus Froude's number square. Froude's number square. We can calculate this Froude number. We know Froude number. It is equal to V square upon under root of GD. It is given that this is a rectangular channel. We know for a rectangular channel, this hydraulic depth, it will be nothing but Y value. So V square upon under root of GY. V square upon under root of GY. Sorry, V upon under root of GD. Just pardon me. This is nothing but V upon under root of GD. So this will also be V upon under root of GD. Or we can directly calculate the Froude number square value, right? As that particular value is needed. So Froude number square value will be V square upon G into Y, at D will be nothing but equal to Y. Clear? Just put the values. Velocity square upon G into Y. Velocity square. Velocity is given as 1.2. Velocity is given as 1.2. Y value is given as 3.7. So Froude number square, it is V square upon G into Y. Y value is 3.7. Give me the value. Give me the value, Prashant. What is the value you are getting? 1.2 square upon G into 3.7. 0.0396. 0.0396. 0.0396. Right? Now, we can find out the dy by dx. That is S0 minus SF upon 1 minus, S0 minus SF that is S naught minus SF upon 1 minus Froude number square. S naught value is given to you 1 by 4000, that is nothing but 0.00025. This will be 1 by 4000 minus 0.00004. This is the second slope, 0.00004 and 1 by 4000. Yes, correct. Right? Divided by 1 minus Froude number square, that is 0.0396. Can you give me the value of dy by dx? Can you give me the value of dy by dx? Can you give me the value of dy by dx? Prashant? This will be 1 by 4000. 1 by 4 is nothing but 0.25 divided by 1000, that will be 0.00025. Give me the value in the terms of 10 to the power minus 4. In the terms of 10 to the power minus 4. 2.18. So it is 2.18 into 10 to the power minus 4. So the answer you have to, the answer which you have to mark will be 2.18 and not 2.18 into 10 to the power minus 4 or 0.00028, right? This is the particular answer which you need to put in this particular gap. I hope it is clear, right? Now the last question of this particular series. Now try to read the question. Just read the question. This will be our last question for today's class, right? Just read the question. It said that a 2 meter wide rectangular channel carries a discharge of 10 meter cube per second at a uniform flow of depth 1 meter. This depth is given at a uniform flow. It means this is the depth y naught, or we have just marked it as a y normal, so I'll write it as y normal only. So this is your y normal. The soil condition suggests that to avoid the erosion, the bed slope should be mild, right? There is a particular channel. If you will increase the slope, the velocity is going to increase, right? And due to that velocity, it is saying that there can be erosion in the channel. So you have to restrict the slope to the mild slope only, right? It should not be critical or supercritical, clear? Or not supercritical or steep slope, right? So it should be either mild or less than mild, clear? If the maximum discharge to be carried is 10 cubic, if the maximum discharge is 10 cubic, then you have to answer. This is now your MSQ type question. It means more than one option can be correct. It is saying that the flattening of channel is required to avoid the erosion. No problem of erosion will occur in the channel. Channel is critical. Channel slope is critical corresponding to maximum discharge. Channel slope is mild corresponding to maximum discharge, right? Now try to figure out. First option, if we see, flattening of channel is required to avoid the erosion. When you have to when you will need the flattening in the channel, if your channel slope it is steeper than this mild. If the channel slope is either critical or steep, then you have to flatten that such that it will be in the mild condition and there will be no erosion, right? It means you just need to check what will be the flow profile or what will be the depth corresponding to this 10 cubic. Corresponding to this 10 cubic, what will be the depth? It means you need to find out the critical depth. Once you will find out the critical depth, you know the normal depth. Based on normal depth and critical depth, you can analyze if the slope is mild, if the slope is critical, or if the slope is your steep, right? So just do that. Normal depth is given to you, that is 1 meter. Right? We know that for a channel to be mild, your y naught value, it should be greater than y critical. Your y naught value should be greater than y critical, right? Now, we need to find out the critical value y critical. So, for a rectangular channel, we can use q square upon g to the power 1 by 3. Q square upon g to the power 1 by 3, right? Now, discharge is given to me and width of the channel is given to me. Discharge is 10, width is 2. Discharge is 10 meter cube per second and width of the channel is 2 meter. So, what will be the Q value? So, Q value will nothing but Q by B, that is 10 by 2 5 meter cube per second. 5 meter cube per second. Right? Per second per meter. Okay? So, YC value if I calculate, it will be 5 square upon G is nothing but 9.81 to the power 1 by 3. Can you give me the value of YC? Can you give me the value of YC? Just calculate the value of YC. It is 6.26. Is there any mistake? Just check the calculation. It is 1 by 3, right? Q square upon g to the power 1 by 3. It is coming to be 6.26 or any other value. 6.26 you are getting? 1.366, right, it is correct. 1.366 meter, right? My normal depth was 1 meter. My critical depth is 1.366. It means your y critical is greater than y normal value. Your y critical is greater than y normal value. Which type of slope? Here y critical is greater than y normal value. Which type of slope? If it is mild, if it is steep, or if it is critical? Tell me, Prashant. Tell me, Prashant, which type of slope it is this? It is going to be steep slope. It is going to be steep slope, right? It means there will be requirement of flattening. When you will flat this steep slope such that it will come to the mild position, right? And then you will be able to avoid the erosion. It means, yes, first option is correct. There will be a flattening of channel is required to avoid the erosion. Second is no problem of erosion will occur. No, there will be a problem of erosion, right? There will be a problem of erosion as the slope is greater than your critical slope. Clear? Next thing is channel is critical corresponding to maximum discharge. Channel is critical corresponding to the maximum discharge. No, it is also not correct. Channel is your steep corresponding to maximum discharge. Fourth option is channel is mild corresponding to maximum discharge. It is also not correct as it is a steep. So only option A is correct. So what will be your answer? Your answer will be option number A. Your answer will be option number A. Clear? I hope it is clear. Is this clear to you? Right. So this is all about the session. I hope it is clear to you. Okay. Right. So we will keep this particular session up to this particular point only. Right. I'll also come live on 14th and 15th of December with geotechnical engineering. Clear? So try to be there. We are going to revise the complete geotechnical engineering through the questions, right? Okay. Also you can visit the IMS Gate Academy for the courses which are launched by us, right? There are different types of courses if we see, right? I'll just give you an insight. So Currently, IMS Gate Academy is offering your 4 type of courses. One is classroom program, where this particular classroom program, it will be completely, yes, hydraulic jump we will discuss, right? But for today's class, it will be up to this particular point only. Clear? Right? So there will be one classroom program. This will be completely online. Sorry, this particular classroom program, it is going to be completely offline program. Right? There is a hybrid classroom program also. This hybrid classroom program, it will be your online plus offline, right? So around 2/3, it will be your offline classes, and 1/3 part it will be your online classes, right? One is exclusively live online program. This is completely online program. You can also enroll in this, right? And there is one self-learning program where you will get the study material, you will get the recorded videos. From that also you can prepare. Clear? So by then, stay tuned with the IMS Gate Academy channel. We'll see you in the next video. Thank you everyone, and good evening again.